one to say the first goodbye. Had to love and lose 100 million times. Had to get it wrong to know just what I like. Now I'm falling. You say my name like I have never heard before. I'm indecisive, but this time I know for sure. I hope I'm not the only one that feels it all. Are you falling? Center of attention, you know you can get whatever you want from me. Whenever you want it, baby. It's you and my reflection. I'm afraid of all the things it could do to me. If I would've known it, baby, I would've stayed at home. Cause I was doing better alone. But when you said hello, I knew that was the end of it all. I should've stayed at home. Cause now there ain't no letting you go. Am I falling in love with the one that could break my heart? Oh no, I was doing better alone. But when you said hello, I knew that was the end of it all. I should've stayed at home. Cause now there ain't no letting you go. Am I falling in love with the one that could break my heart? I wonder when you go if I stay on your mind. Two can play that game, but you win me every time. Everyone before you was a waste of time. Yeah, you got me. Center of attention, you know you can get whatever you want from me. Whenever you want it, baby. It's you and my reflection. I'm afraid of all the things it could do to me. If I would've known it, baby, I would've stayed at home. Cause I was doing better alone. But when you said hello, I knew that was the end of it all. I should've stayed at home. Cause now there ain't no letting you go. Am I falling in love with the one that could break my heart? Oh no, I was doing better alone. But when you said hello, I knew that was the end of it all. I should've stayed at home. Cause now there ain't no letting you go. Am I falling in love with the one that could break my heart? Break my heart. Break my heart. Am I falling in love with the one that could break my heart? I would've stayed at home. Cause I was doing better alone. But when you said hello, I knew that was the end of it all. I should've stayed at home. Cause now there ain't no letting you go. Am I falling in love with the one that could break my heart? Oh no, I was doing better alone. But when you said hello, I knew that was the end of it all. I should've stayed at home. Cause now there ain't no letting you go. Am I falling in love with the one that could break my heart?
Billboard, baby, do a leap and make them dance when they come on. Everybody looking for a dance floor to run on.
If you wanna run away with me, I know a galaxy and I could take you for a ride. I had a premonition that we fell into a rhythm where the music don't stop for life. Glitter in the sky, glitter in my eyes, shining just the way I like. If you're feeling like you need a little bit of company, you met me at the perfect time. You want me, I want you, baby. My sugar boo, I'm levitating. The Milky Way, we're renegading. Yeah, 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 yeah. I got you, moonlight. You're my starlight. I need you all night. Come on, dance with me. I'm levitating. You, moonlight. You're my starlight. I need you all night. Come on, dance with me. I'm levitating.
I'm one of the greatest, ain't no debating on it. I'm still levitated, I'm heavily medicated. Ironic, I gave him love and they end up hating on me. She told me she loved me and she been waiting. Been fighting hard for your love and I'm running thin on my patience. Needing someone to hug, even took it back to the basics. You see what you got me out here doing? Might have threw me off, but can't nobody stop the movement. Let's go. Left foot, right foot, levitating. Pop stars, do a leap with the baby. I had had to lace my shoes for all the blessings I was chasing. If I ever slip, I fall into a better situation. So catch up, go put some cheese on it, get out and get your bread up. They always leave when you fall, but you run together. Weight of the world on my shoulders, I kept my head up. Now baby, stand up, cause girl, you
want me, I want you, baby. My sugar boo, I'm levitating. The Milky Way, we're renegading. Yeah, 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 yeah. I got you, moonlight. You're my starlight. I need you all night. Come on, dance with me. I'm levitating. You, moonlight. You're my starlight. I need you all night. Come on, dance with me. I'm levitating. You can fly away with me tonight. So you can fly away with me tonight. Baby, let me take you for a ride. Yeah, 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 yeah. I'm levitating. You can fly away with me tonight. So you can fly away with me tonight. Baby, let me take you for a ride. Yeah, 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 yeah. My love is like a rocket, watch it blast off. And I'm feeling so electric, dance on our stop. And even if I wanted to, I can't stop. Yeah, 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 yeah. My love is like a rocket, watch it blast off. And I'm feeling so electric, dance my ass off. And even if I wanted to, I can't stop. Yeah, 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 yeah. You want me, I want you, baby. My sugar boo, I'm levitating. The Milky Way, we're renegading. I got you, moonlight. You're my starlight. I need you all night. Come on, dance with me. I'm levitating. You can fly away with me tonight. So you can fly away with me tonight. Baby, let me take you for a ride. Yeah, 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 yeah. I'm levitating. You can fly away with me tonight. So you can fly away with me tonight. Baby, let me take you for a ride. Yeah, 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 yeah. I got you, moonlight. You're my starlight. I need you all night. Come on, dance with me. I'm levitating.
It's beautiful, it's bittersweet. You're like a broken home to me. I take a shot of memories and black out like an empty street. I fill my days with the way you walk and fill my nights with broken dreams. I make up lies inside my head like one day you'll come back to me. Now I'm not holding on, not holding on. I'm just afraid to show up on. Not holding on, not holding on. Beautiful mistakes I make inside my head. She's naked in my bed, and I will lie awake, making beautiful mistakes. I wouldn't take them back. I'm in love with the past, and I will lie awake, making beautiful mistakes. Na na na, in my head. Na na na, in my bed. Na na na, making beautiful mistakes.
You did me wrong cause I let you. Usually I like my situations beneficial. Doing something different, got me looking stupid. The only way I'm coming back to you is if you're dreaming. Lucid, prove it. If you made a promise, then keep it. Why you wanna lie and then get mad? I don't believe it. But really, I was doing just fine without you. Looking fine, sipping wine, dancing no club couches. Baby, why you wanna lose me like you don't need me? Like I don't block you and you still try to reach me. How you figure out how to call me from the TV? You running out of chances and this time I mean it.
Mistakes I make inside my head. She's naked in my bed, and I will lie awake, making beautiful mistakes. I wouldn't take them back. I'm in love with the past, and I will lie awake, making beautiful mistakes. Na na na, in my head. Na na na, in my bed. Na na na, making beautiful mistakes.
Bet you miss my love all in your bed. Now you're stressing out, pulling your hair, smelling your pillows and wishing I was there. Sliding down the show wall, looking sad. I know it's hard to let go, I'm the best. Best you ever had and best you gon' get. And if we break up, I don't wanna be friends. You're toxic.
Beautiful mistakes I make inside my head. She's naked in my bed, and I will lie awake, making beautiful mistakes.
Check, check. Can everyone hear me? Welcome everyone. We'll get started in another 10 minutes. Please feel to grab refreshments and take a seat. We should get started by in about 10 to 15 minutes. waiting for more people to come in. Test. Now can everyone hear me? Yeah, okay.
We don't talk anymore. We don't talk anymore. We don't talk anymore like we used to do. We don't laugh anymore. What was all of it for? Ooh, we don't talk anymore like we used to do. I just heard you found the one you've been looking for. I wish I would have known that wasn't me. 'Cause even after all this time I still wonder why I can't move on just the way you did so easily. Don't wanna know the kind of dress you're wearing tonight, if he's holding on to you so tight, the way I did before. I overdosed, should've known your love was a game. Now I can't get you out of my brain. Oh, it's such a shame that we don't talk anymore. We don't talk anymore. We don't talk anymore like we used to do. We don't laugh anymore. What was all of it for? Oh, we don't talk anymore like we used to do.
I just hope you're lying next to somebody who knows how to love you like me. There must be a good reason that you're gone. Every now and then I think you might want me to come show up at your door, but I'm just too afraid that I'll be wrong. Don't wanna know if you're looking into her eyes, if she's holding on to you so tight, the way I did before. I overdosed, should've known your love was a game. Now I can't get you out of my brain. Oh, it's such a shame
that we don't talk anymore. We don't talk anymore. We don't talk anymore like we used to do. We don't laugh anymore. What was all of it for? Oh, we don't talk anymore like we used to do. Dress you're wearing tonight, if he's giving it to you just right, the way I did before.
I overdosed, should've known your love was a game. Now I can't get you out of my brain.
Oh, it's such a shame that we don't talk anymore. We don't talk anymore. We don't talk anymore like we used to do. We don't laugh anymore. What was all of it for? Oh, we don't talk anymore like we used to do. We don't talk anymore.
The way I did before.
We don't talk anymore.
Oh, it's such a shame
that we don't talk anymore. I don't want this night to end. It's closing time, so leave with me again. Yeah, you got all my love to spend. Oh, let's find a place where happiness begins. We're gonna dance in my living room, slave to the way you move, hurts when I'm leaving you. Just dance in the living room, love with an attitude, drunk to an 80s groove. We're gonna dance in my living room, slave to the way you move, hurts when I'm leaving you. try to deny the way that you feel. Oh baby, can't fool me. Nobody's got other plans, so stop pretending you're shy. Just come on and dance, 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 dance. Oh. Early morning, la la light. Only getting up to close the blinds. Oh, I'm praying you don't change your mind, 'cause leaving now just don't feel right. Let's do it one more time. Oh, baby, come dance in my living room, slave to the way you move. Hurts when I'm leaving you. Just dance in the living room, love with an attitude, drunk to an 80s groove. Hey, we come dance in my living room, slave to the way you move. Hurts when I'm leaving you. Hey, dance in the living room, love with an attitude, drunk. It's only you, man, you know that it's real. So why would you fight or try to deny the way that you feel? Oh baby, you can't fool me. Nobody's got other plans, so stop pretending you're shy. Just come on and dance, 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 dance. Oh, hey, only human. It's only human. Oh yeah, yeah, yeah. Only human. It's only human.
Can everyone hear me? Welcome everyone. We'll get started in the next 5 minutes, so please feel free to grab refreshments and find a seat. Maybe 5 more minutes.
Think that I'm a fool. You must think that I'm new to this, but I have seen this song before. I'm never gonna let you close to me, even though you mean the most to me. 'Cause every time I open up it hurts. So I'm never gonna get too close to you, even when I mean the most to you, in case you go and leave me in the dirt. But every time you hurt me, the less that I cry. And every time you leave me, the quicker these tears dry. And every time you walk out, the less I love you. Baby, we don't stand a chance. It's sad, but it's true. I'm way too good at goodbye. I'm way too good at goodbye. I'm way too good at goodbye. I know you're thinking I'm heartless. I know you're thinking I'm cold. I'm just protecting my innocence. I'm just protecting my soul. I'm never gonna let you close to me, even though you mean the most to me. 'Cause every time I open up it hurts. So I'm never gonna get too close to you, even when I mean the most to you, in case you go and leave me in the dirt. But every time you hurt me, the less that I cry. And every time you leave me, the quicker these tears dry. And every time you walk out, the less I love you. Baby, we don't stand a chance. It's sad, but it's true. I'm way too good at goodbye. I'm way too good at goodbye. I'm way too good at goodbye. No way that you'll see me cry. I'm way too good at goodbye. No, 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 no.
I'm way too good at goodbye. Hello, everyone. Good afternoon. Happy Friday. Welcome to the Big Data Meetup. And uh, I'm really excited to be here as your co-host. My name is Swati. I'm a senior manager at LinkedIn. I've been here for about 4.5 years, and I support the data lake tables and views team. And you'll hear some of the work that my team is doing during the course of this meetup. Outside of work, I have a 12-year-old that I like to spend time baking and making art with. And in my copious free time, which I don't have enough of, I volunteer as an art teacher in my local school district.
And I'm Eric. I'm happy to be co-hosting today with Swati. I've been a software engineer here at LinkedIn for coming up on 8 years, working in our kind of across our big data stack, most recently in our compute infrastructure, specifically kind of Trino and Spark. I wasn't prepared with an outside of my free time, so I'll pass on that one.
Cool. Thank you, Eric. So before we get started, just a few housekeeping reminders. Please keep your questions coming towards the end of the talk. We have a mic out here in the middle. If you could approach the mic and line up behind it, that would be great. Put your phones on silent. And for anyone that needs to use the restroom, there's signage. The restrooms are located over there, or please talk to one of the volunteers in the back. They can help. And we have food and refreshments out in the back. Networking should start at around 4:45 p.m. And also be prepared for trivia questions. For trivia, I would request you to raise your hands when we ask the questions. We have swag. So we'll be testing whether you're paying attention to the talks. Just kidding. All right, so this is a brief agenda. We have really, really exciting talks lined up. I won't go through every single one of these. Eric will be doing the intro for each of these talks. Okay, with that, so to wake everyone up, let's start with trivia. Christy over here is holding up the trivia swag. All right, with that, let's get started. Okay, what is the approximate size of LinkedIn's economic graph? Is it 10 billion edges, 1 billion nodes, 10 billion edges and 10 billion nodes, 200 billion edges, 1 billion nodes, or 200 billion edges, 10 billion nodes? Okay, who wants to go first? Raise your hand, don't be afraid. Yes. C, you're correct. Yes, the right answer is nearly 200 billion edges, 1 billion nodes. Awesome. As of April, I think April 23rd, but cool. Awesome. I think hopefully everyone's awake now. And where do you, Eric?
Okay, so we're going to start off with a joint talk. We have folks joining us today from Microsoft, as well as LinkedIn and OneHouse. So a little bit about the speakers we have today. So we have Ashwin Agarwal from Microsoft. He's a principal research engineer in Microsoft Gray Systems Lab, focused on data storage and provenance and distributed databases, and has a long history in open source software, including HDFS, Apache Geode, Heron, and Xtable, which we'll hear a bit about today. Also from Microsoft, we have Jesus Camacho Rodriguez, principal research manager also in GSL at Microsoft, with a focus on optimizing data system performance and efficiency, and also with a very long history of open source software involvement, including Calcite, Hive, and again, Xtable. Joining us from LinkedIn, we have Lei Sun. He's a staff engineer at LinkedIn who has worked across the data domain, including ingestion, compliance, and file formats, and has spent the last 3 years focused on building Open House at LinkedIn. And finally, we have Deepankar Mazumdar joining us from One House, not to be confused with Open House, focused on open source projects like Hoodie and Xtable, and with previous involvement in the Iceberg and Arrow open source projects. So with that, I'll pass it off to Jesus.
Awesome. Thank you so much. Can you hear me? Okay, good. Let's go. Okay, my name is Jesus. I come from GSL at Microsoft, and I'm going to start this talk about table formats by covering a little bit an overview, motivation, and some of the stuff we've been doing at GSL, in this area. So first, a little bit of motivation, right? Over the last, 10 years or so, we see more and more kind of a shift towards a data lake-centric architecture, right? Where you will have multiple engines kind of interoperable, working on top of a single data lake storage, right? And it's not surprising why customers and users like this type of architecture, right? Because it brings multiple benefits. For instance, you will have a flexible scalability in the sense that you can scale independently your storage and your compute, and you will have more efficiency, more cost savings, and so on. You also can have a streamlined workflows, right? So suddenly there is an elimination of data silos. You can have you have less data movement, less data copying across engines because they can work on the same copy of the data, right? Also reduce locking. So now, once again, because any engine can access the data storage directly, now you have more flexibility to choose like the best engine for your application or even for each step in your workflow, right? If you want to know a little bit more and go a little bit more in detail, I recommend this kind of white paper fresh off the press that is Open Lakes, Not Walled Gardens, that is written by Raghu Ramakrishnan, who is the CTO for data at Azure at Microsoft, and Josh Kaplan, who is the PM responsible for OneLake, that is the data lake in Fabric, in one of the new Microsoft offerings. But now there are challenges as well, right? So now you have these multiple engines in kind of interacting with a single storage layer. You're going to have complex read and write transactions that require guarantees like consistency and isolation. And these data lakes, based on HDFS or object stores, while they excel on scalability and durability, they lack the necessary concurrency and recovery capabilities to offer these guarantees, right? So that's where table formats or log structured tables, or LSTs, how I will call them throughout this talk, come in, right? So these are popular open source projects such as Delta, Hoodie, Iceberg, that I'm sure most of you have heard about, that provide this additional functionality like transactions, indexes, time travel, cloning, and many more on top of a low-cost data lake storage. And now, they all kind of share same goal, but the architectural implementation is slightly different across them, right? And each of them is going to have its own strengths. Different implementations for metadata caching, distributed planning, different trade-offs in terms of copy on write and merge on read support, different storage optimizations and so on. And very importantly, it's not only about the table format itself, it's also about the integration with the engines that is going to affect the kind of behavior and performance you're going to get on top of these table formats. Now, here what we're showing is the anatomy of each of these table formats that I was describing: Delta, Iceberg, and Hoodie. It's quite small, and I'm not going to go into detail in each of them, but I'm going to highlight certain things or certain common pieces that the three of them have, right? This is reverse. Okay, let me go do it this way. One of them is the data lake, right? So bottom right. So there, what you have is your, open file formats like Parquet, like ORC, columnar optimized, and what you're going to have is a different layout, depending on how you're partitioning your data, clustering your data, also depending on whether you're using copy on write, where each change is going to create a new copy of the data versus merge on read, where you are consolidating at read time, right? And this layer, how you kind of lay out your data in your table, is going to have a huge effect on performance, cost, etc. The second one is the metadata, so bottom left. So this one really what is doing is keeping the different versions of or snapshots of a table, right, and how they evolve over time. And for each snapshot, you're going to have pointers to your data files. They also keep things like statistics, column statistics, and so on. So they really affect the query plan quality and so on. But now one key insight here is that the type of metadata, although how they structure it is different, the type of metadata that they store is very similar across the three formats. And that key insight is important because one might wonder whether you can kind of go from one format to another just by translating the metadata. And that's basically the foundation of a project that is called Xtable that Ashwin and Dipankar will talk about in the after me. And now the third part at the top is the catalog layer. So catalog layer kind of encompasses a lot of functionality. One of them, for instance, is the transactions and concurrency, right? So it will keep pointers to the latest snapshot of the data, and it will have to, as transactions are coming in, it will have to, control the concurrency across users and see how that table is evolving over time. There are also some other concerns, such as governance, that usually belong to the catalog layer. Some catalogs also implement services like data compaction and so on. And one thing also I want to highlight is that these formats also are not opinionated in terms of the catalog that you should use. So you can have even for each of these formats different catalog implementations, which again creates fragmentation. And that's where a project that LinkedIn has been working on, Open House, is coming in, and Lei will be talking about it later on in this presentation. And now, we have this beautiful picture, very clear separation, but the truth is that things are slightly more complex. How all these layers interact together, that's what is going to affect end-to-end performance, the end behavior that you're going to get, together with the interactions with the engine and so on. Now, talking about performance itself, performance is not the only aspect that people look at when they say, okay, I'm going to use in my organization table formats, right? But it is one of them. When we started this journey at TSL a couple of years ago, we started looking at, okay, how are people evaluating the performance on these table formats, on these engines and so on? We realized that people were commonly using benchmarks such as TPCDS to do this. But this approach has drawbacks. And we highlight there two main ones, right? One is that the TPCDS workload overlooks critical characteristics of LSTs and engines in real-world scenarios. So what this means is, if you take TPCDS, you have two phases of 99 queries, and in between, you will have a data maintenance phase that will alter around 3% of your data. Now, if you go to the lake, you might see patterns, for instance, where you have much more continuous ingestion, inserts, trickle updates, and so on, right? So that's not covered by TPCDS by default. The other part is also that it lacks the metrics to evaluate LSTs or some of the characteristics of the LSTs. And what I mean with this, TPCDS will have these queries per DS, and it has some metrics around pricing and so on. But it lacks, for instance, metrics that can tell us, okay, how stable is a table format over time? How much my performance is going to degrade as these trickle inserts come in? They create fragmentation on my storage layer, and suddenly my engine starts going slower, right? And that's also where services around table formats also play a very important role, right? In order to kind of solve this, what we did is propose an LST bench that is a benchmark tool that is specifically tailored to evaluate LSTs. where we propose new workload patterns for LSTs, but most importantly, we make it very easy for anyone to create their own patterns, and also some metric extensions, right? Nowadays, it's integrated into this new offering of Fabric data warehousing in the testing pipeline in order to catch regressions, see again how system degrades over time and so on. There is a paper that will be presented at CMOD in a couple of months. If you want more details, please check it and get back to us. Now, I don't have time to cover LST bench in detail, but I want to show two things, okay? One of them is related to the workload patterns. So I want you to look first at the top right. So you have at the top right, you have the traditional tasks that could, or phases that could be executed on TPCDS. You have load that will basically take your external data and dump it into your managed tables. You have single user phase that basically what we'll do is execute some permutation of the 99 queries of TPCDS. You have a data maintenance phase that is the one that will do the data modifications on the data. And what we did is, okay, let's start with this model. Let's see what we need to extend in order to be able to create new workload patterns, right? So first of all, we introduce some tasks that are specific to LSTs, right? For instance, an optimize that basically what it's doing is running compaction on top of the data. Single user with time travel, so run the 99 queries, but back into a certain point in time. Or custom tasks that can dynamically generate some other tasks to kind of provide flexibility for users to create their own patterns. And now, what can we do with that, right? So now, if we have this question, okay, how are frequent data modifications handled over a long period of time by my engine on top of a certain table format? I don't need to execute just 2 single user and data maintenance phases. Suddenly, I can chain them and kind of do this kind of longevity test to evaluate how well the engine is performing in these cases, right? Or the system is performing in these cases. We can also answer, okay, if you have multiple modifications over time that they are kind of varying in sizes, so you can see that the data maintenance, let's see if this is working. Well, maybe not. Okay, so the data maintenance phases, you can see that they are growing over time, and then you see the compaction in between, and you have a single user before and after. So if you compare single user phases before and after, you can see how effective is my compaction in bringing the table to my original state. What about concurrency, right? Okay, so you can, for instance, execute on one engine only a single user read task, while the other engine is running all the gripes on my lake, all the modifications. This is the one where we can use kind of custom tasks. So how does updating or deleting the same data volume, but in different batch sizes, influence read query performance? So if we want to delete the data of a partition, we don't know the size. If we want to create batches, these need to be generated dynamically depending on the size of your partition. So basically, that's what the custom task will do. It will generate an task dynamically that will do the data maintenance, and then you can run a single user phase on top. And finally, this one is kind of straightforward. How is data querying across different points in time handled? So I know this is kind of a lot of different workflows, but I think bottom line, what you can see here is these ones are by default already part of LST Bench. If you want to create your own, it's also very straightforward. You can do it simply by changing kind of configuration files and so on. And that was one of the goals that we had in mind when we work on this. And to conclude, just a little bit of details on how this is implemented. So it's a Java client. It has 2 modules. One is a Java client application that, again, you can create all these patterns via config files, no need to change really the code. It will connect to the engines either via JDBC or Spark Session Client. In case of Spark, there is also this option. Then there's also a Python metrics processor that what it does is gathers the telemetry that this LST Bench client application is emitting, and also it correlates with some of the telemetry that the cloud services, the engines might be emitting to get further insights through a kind of a visualization app. So this is all open source. It's under Apache license, so go there, test it, provide feedback. Contributions are welcome, of course, and so on. So with that, I lean into Ashby, who is going to be talking about interoperability and Apache Xtable. So thank you, Ashby.
Thanks, Jesus. You can hear me clearly? So what Jesus was talking about is the table formats, mutable tables, which are popular in data lakes these days. These are not transactional tables, but they have more updates than what analytical bulk upload tables used to be in previous generation. So they are special tables, and we have 3 open source formats which are very popular. The way they evolved, the way they are designed, the use cases which they started with, they resulted in the strength these table formats have. So different workloads will result in different requirements, and different table formats will have their own advantages which users would like to use. But the goal of all this is that there is a single copy of data which users want to maintain. Data duplication is costly, is error prone, it doesn't work anymore, given the volumes of data, right? And the other thing is that we want to improve data sharing as well as much as possible. So although we have strengths of these table formats and they operate at different efficiency in different cases, there is a cost. And these table formats, open source, also will create some fragmentation, which is the problem which we are trying to address with Xtable. Xtable is an Apache project. I'm working with some brilliant people. And I'm one of the Apache PMC members, and I'm also working with Jesus in the GSL lab at Microsoft. So before I get into the Xtable details, let me motivate by what we are doing, what are the common patterns which we are seeing in different implementations. So the idea is that we unify at the compute layer, the unification at the storage layer, which is promoting more of this data, the trends we are seeing these days. And as an example, I come from Microsoft. I'll show what Microsoft Fabric is doing in this particular case. So what we have done is that there are multiple compute engines. There's a SQL engine, there's a notebook engine, Spark is there, there's Power BI, there are Gusto, there are a lot of engines are there. All these engines, instead of trying to connect them with different kind of table formats or different kind of security credentials and all, the fragility which comes with integration, that is taken away by Fabric. All the compute engines, they speak to one lake, which is the unified storage layer. And on top of this, currently they commit to the Delta Lake format. What it means is that the table which is created once can be read by any table. There is no data copy, there is no fragmentation anymore. A lot of work went into this and just to improve this thing. And after that, we extend the Fabric engine, also the platform extend. And this is not common to Microsoft. There are other platforms also which provide some of these features. So this is an emerging trend, very common trend. Fabric also extends it beyond just unification of the compute, that the compute can operate on the same copy of data, but it also allows user to bring data from external engines. So external storage accounts. For example, it could live in a different cloud storage, it could live in a storage account, it could live in on-prem storage engines account. In Microsoft Fabric, it is called a shortcut. People call it mount points, links, or some by other names. So what you see on the screen is that when you go to Fabric, users can just provide a link to the location where the table is stored. As long as the table is in Delta Lake format, Fabric, any engine in Fabric will be able to read it. So what we see here is that a link is provided. Users will go and select the tables they are interested in. And one lake would provide a unified view to the user. So if a data scientist is there or engineer is there, for the user the user doesn't need to know where the table is coming from, where the credentials stored, and anything like that. There is one view. On top of this view, the user can create a SQL query, run the SQL endpoint on it without knowing where it's coming from. Fabric engine will provide some enhancements to speed up the query execution, even if it is living the data is stored in a different storage account in a different region. The data would be cached in wherever required and so on, so that the performance is reasonable. What you saw here is a SQL query. User can also go to the notebook and create a more complex experience on top of this. Or if the user wants, they can also create more relationships between these tables, irrespective of where the data is stored, which storage account it is stored in, and who created the data, which engine created the data. So the relationships can be created. And this is very useful when you're creating more experiences on top of it, like the Power BI report. So once the semantic model is created, user can go to Power BI and create beautiful dashboards on it. And this information is shared by all engines in the Fabric ecosystem. Going beyond that, it's just not the sharing of the compute or sharing of the storage layer, but user can also see the entire lineage of how this data state was built. So you have unification at the data state, irrespective of where the data is coming from, but also how the data was created. Is it trustworthy enough or not? So lineage is there, and this is what the Fabric engine brings together, and other engines also doing it, as I mentioned earlier. So the point is that this was all enabled by all these engines supporting an open storage format for a table representation, right? So the engines, they are tuned and they are tested for working with some preferred table formats, and it enabled this experience for the user. However, there is a limitation still. The problem is that what if the data is not in Delta Lake format, right? There are some engines which support Iceberg, there are other engines which produce Hoodie. So if that is the case, then we still have fragmentation. And that is what we are trying to solve with Apache Actionable project, which is a collaboration with various companies here. And all of them understand it. There are a lot of companies which are building their own translators from Delta to Iceberg or so on. But this Actionable project is an initiative which we have combined together. And the goal is that we allow users to translate between these table formats so that we still can honor the original requirement that we do not have multiple copies of the data. So as Jesus mentioned earlier, the metadata layer, which is a central layer, it is responsible for the quality of the query plans which are created by various engines, because this is where the statistics are stored, partition information is stored, and so on. However, this is the layer which is responsible for the incompatibility between table formats, various LSTs. And that is what is getting the lock-in, which is going against the unification trend, which is what the users need right now. However, we do know that the representation of metadata is different. Still, what is good is that the contents of this metadata is more or less the same in all of these table formats, whether this open source or even if proprietary formats are created, the contents are more or less same. So if I double click on the contents here, the most important thing is that instead of going to a storage account and doing a list call, which is very expensive, usually all the file paths are stored in this metadata layer. Schema information is there, partition information is there, how the table evolved, various transaction logs are there, who did it, and so on, and statistics and governance information. So all these table formats in general have this information represented differently. So we leverage this point that these table formats have this information, and what we do is we build Xtable, which is okay. So we build Xtable, which will use this information, read it in one format, and generate any other format which is possible. So because we are operating only on the metadata layer, and just to give you some reference, like if you have 1 terabyte of TP-CDS table, which Jesus created using LST bench, the size of metadata will be less than 100 MB. So if I have to read 100 MB and write it in a different format, it is much faster, much lower overhead than instead of copying the data from Delta into Iceberg or so on. This is omnidirectional. What it means is that you do not have to deploy 3 converters, one to convert Delta to Iceberg, second to Iceberg to Delta, and then Hoodie to Iceberg, and so on. So omnidirection, we allow conversion in any direction in Xtable. It is extensible. If I have a proprietary format, we have abstracted some APIs, just extend those APIs, and then we can create an n-by-n metrics using any formats as well. Incremental, we can detect what changes are happening on the table, source table, and only those commits which were added after the previous conversion will continuously keep updating them on the target table. That way, it's not a one-time task. It's continuously, we have 2 views of the same data in 2 different table formats, always up to date and in sync. And finally, it is flexible. Right now, if you go to the open source library, it is a command line operation, but it could also be integrated, a library can be integrated into a service or in a function and so on. So there are a lot of features which are already built into this. The exact architecture, some of the further details, Dipankar will show in his demo. This is an Apache project. We started in December. I'm very happy that we have got a lot of traction in the industry. We have more than 650 GitHub stars and all. And just to repeat, this Xtable is a translator. Okay, we are not building a new table format. The last thing we need is another table format to solve a problem of 3 table formats. So it's not a table format, it's just a translator. And it does not touch the data files. So if the data files are not optimally designed, the layout is not optimal, they are too small, or they are not ordered properly, then the performance impact will not be because of Xtable. So the query performance depends on the data files. Xtable does not touch the data files. There will be no degradation or improvement in performance because of Xtable data files that they are placed. Okay, because we do not even see the data in Xtable, we do not generate new stats. So the query planner will not benefit from it just as of now. Okay, maybe in tomorrow we'll have some more improvements in Xtable and we'll add these features as well. And finally, Xtable does not do table maintenance. So if you detect there are too many commits which could be compacted and all, Xtable currently does not do it. That's a role which Open House will eventually solve. So this is in general about Xtable high-level features. We want more and more people to come and contribute and join us in this initiative. And to go more into details, exactly what I was talking about, let's see something in action, and Dipankar will show us that.
Let's get to it. Just give me a moment. I'm gonna put this up in the main screen. All right. Thanks everyone for joining, and thank you so much, Ashwin and Jesus, for kind of like setting the context right here. So my name is Dipankar, and I kind of contribute to Hoodie now. Previously, I was working with Iceberg and Arrow as well. So right now, I also like focus on Xtable and have been like trying to learn more and grasp more about it and like contribute more. So like Ashwin mentioned, it's Xtable is a lightweight kind of translation layer that provides that omnidirectional interoperability part. So this means we are not just limited like to one format and like kind of like even do like a round trip conversion and like a round robin kind of fashion thing. So the most important thing that we kind of Ashwin does here is that we are not like touching the data files here and like rewriting the data files or something. We're just only walking through like the metadata part of it because that's where like the things are a bit different. So I'm going to talk a bit about Xtable's architecture. So in general, we have this high-level overview, and if you're interested, there is a preprint publication as well, and I can share it later. But in general, Xtable consists of three important parts. One is the conversion source, the conversion target, and the kind of the logic, the core kind of like the logic when what happens beyond that. So the first part is the conversion source itself, which is basically like they are kind of table format specific like modules, and they are responsible for reading the metadata from the source format and extracting information like schema information, transactional information, partition related info, and they basically translate into kind of an internal representation, which is basically done in like the logic part, and that's where like it's represented in kind of a unified model. And the second part is basically the logic itself, which is like super important. It's kind of the CPU of Xtable, if you may. So it orchestrates kind of the entire translation process, right from like setting up the configurations and initializing the components, managing these different source and target formats, and handling like tasks like caching, incremental processing, and those kind of things. The final part is basically the target part, which basically mirrors the source part. Like if you see in the diagram, I don't know how visible is it, but yeah, you can see the kind of the source extractor, and it's the schema extractor. You can see the schema writer, so it mirrors that. And its kind of main role is to take that internal representation and accurately kind of map it to the target table format structure. And again, this includes like regreeting like the transaction logs, the schema, the partition, and all those kind of things. So I'm going to quickly like switch over and like show a demo. I hope the demo runs. You know how demos are typically. But basically, what we're trying to do here is that right now, Xtable, how it works is we have a config YAML file where you define your source and the target format, and then you can run a jar file as of now. So I see this particular thing over here, so I'm going to pull it up again over there. All right. Yeah, so this is what I'm talking about in terms of like the YAML file itself. So you define your source format as Hoodie, the target format is Delta, and your whatever it is. It can be Iceberg as well. You can just put a more parameter there, and you put the table base path and the table base name. So I'm going to like go over a hypothetical kind of a scenario here, and hopefully that kind of sheds more light in terms of like how interoperability is important here, right? So here you can see like I put everything together here, but in a more like a real world, you would see like two disparate kind of data teams working on two different things. So for example, one of the team, they work with like Spark and Hoodie. They have a lot of pipelines with Hoodie. And the reason they use Hoodie is because it's great with upserts, like more ingestion, better performance in that part. and yeah, they write it to Hoodie as one of the data set, right? It's very simple, and the whole idea behind is just to like focus on the interoperability part. And then there is a team B of like data science engineers, more on the analytical level, and they are the one who are basically like trying to use Dataframes or any kind of compute engine for the matter. In this case, I have Daft. Shout out to Daft here as well. It's a distributed data frame, and basically the whole idea is that they are in general not concerned about the table format part. They're abstracted in a way, but also all of their pipeline runs in Delta. Let's say for this hypothetical scenario, it could be something else. So they have maybe a lot of Ray cluster. They're like doing like building SAML pipelines and those kind of things. So they want to just read this particular table as a Delta table, the other data set that was generated by the other team, right? So in this case, what Actionable does is we specify the source table format as Hoodie, target as Delta. We're going to see some kind of a translation over here. So one other thing is here, the S3 bucket itself. I want to show you the metadata part of it. So that it kind of gives an impression, right? So I'm not going to run the ingestion job here. It might take a bit while. It's a small data set, but still. So you can see here like the Hoodie metadata here, right? You can see the Hoodie metadata folder here. That's the kind of like the picture that you saw from the 3 different table formats there. And you see the Parquet files, what are the actual data files that are being written as part of the Spark ingestion job here. So what we expect to see here is basically what Actionable would do. You would see if you like specify Delta or Iceberg as a format, you'd see like Iceberg specific metadata, the manifest list or the metadata file, whatever it is, and Delta transaction log here. So all I have to do here in this case is basically, I'm going to pull up the CLI here because I have a CLI. Okay, I can see it here. All right. Right, yeah. All right, so what I'm trying to do here is basically run this, the jar file here. So I'm going to just run this particular thing and hope that it runs fine. So in the process, what happens is like Actionable is, okay, yeah, it could be working. I can't see much. Okay, yeah, it says it's running sync. So basically, it's just this is the first time we are syncing. So initially it says the no previous Actionable. It says one table here, but we gotta change the name here. But it's kind of like no previous sync was found, so it falls back to the kind of full sync mode. So Actionable does allow another mode of syncing, which is like incremental mode. So you don't have to really like for example, like you can do a commit by commit like syncing. So you can basically like go and like take. You don't have to like do a full sync again if you want to. So here it says no previous sync found. So that means it's going to do like a full sync here. And yeah, in the background we're seeing like some more process happening. But hopefully we'll be able to see like the metadata in a few seconds probably, unless we hit something. Okay, perfect. So it says one table sync is or Actionable sync is successful for the following tables. And if I now go to my S3 bucket, I should see the Delta transaction log over there. So yeah, so if I go and refresh this particular, okay, I see the Delta log here. And that's basically the metadata rewrite, the metadata change that has happened here without touching the data files here. So if you are into like, if you are the other team who are using like Daft for your analysis part, what you could basically do is you can just say, hey, I want to just read this particular as a Delta table. They don't care, right? You want to use it for analysis. So you can just pull it up and, Daft does the thing. And it presents, you can see the Hoodie, like, meta fills here, although it's a Delta table. So it's really like, it's in a way you can use it for analysis. And as the team goes, you can like scale it up for your workloads. You can build your visualizations. You can build your model, whatever it is. Like, so that's what basically Actionable does. So that's the kind of the a very like lighter form of demo, but obviously at scale, and we will have like different workloads, a lot of maybe larger tables. So there are certain like nuances around that as well. One last thing before I end this particular part. All right. Okay. Okay, so we started Actionable or one table like with this idea of like, okay, how can we like bring this different metadata together and make sure like there is no fragmentation in a way, but also like we're in a kind of nascent stage, if you may, like, and we have a really good momentum here, and we see like a lot of active contribution. Companies are adopting that particular thing, specifically like data platform teams who really provide data to different organizations. So in terms of the improvements, what we're looking at is that we want to keep building on it, and right. But here's some of the things, right, today. Basically, Actionable provides interoperability at the metadata layer today. But over the year, maybe, or then in the next phase, we want to like extend this to other layers that we discussed about, catalog, for example, or the data layer part as well. Then next, the performance improvement part, right? Today, when we load the source table data, we keep it in memory for some time. And that may be kind of a little bit of overhead in a way when you have a more larger table. The third part is basically, you want to be able to increase increase your load without compromising your performance part, and also, at the same time, keep your kind of costs reduced in a way. Another feature which is super important as well, and we are looking into some of the important things, for example, like deletion vectors in Delta, like merge and read. So feature parity between different formats would be something super interesting to bring it together. And finally, of course, the stainless is an important part, because right now what happens is like we do a polling of the particular source target format to the source format to understand what has been changed, and that can take some time typically. And it also depends on the strategy, right? For example, like in your organization, you might run a job or something at this point of time, where you want to okay, I have Iceberg in this particular format and I have the latest commit now. Now, how do I run it in a particular interval, right? And over the years, maybe deployment as a service could be super interesting as well, because right now it could be like a cron job or a Lambda kind of event vector or something. So that's my talk, and I'll hand over to Lei, who's going to talk about open house and the catalog part as well. Thank you so much.
You hear me? Okay, I think it's working. Hi everyone, my name is Lei. I'm going to talk about open house. So specifically, it's about our experience of hosting Iceberg table using open house at LinkedIn Scale. So a quick overview of open house. What exactly is open house? We internally call it control plane, but what it really means are just three components. The first thing, which is most important one, is control plane API. So what this thing provides you is just a standard set of catalog operations. You can do get table, put table, listing table. The second part of the API, which I'm going to talk a little bit more in details as well later, is sharing. So we provide a SQL-based sharing for you to programmatically share the table you created to other folks. And the last part is what we call declarative table management. I also have another slide talking about this, but this is very relevant to the first point for the next components called data services. But to simplify, data services is just a bunch of applications or jobs to making sure your tables are in good shape. So one example is state reconciliation. So you can think of this like you can declare a table to be certain state, and open house is responsible to making sure your table reaching that declared state. So example that I'm going to cover later is retention. Other example of such activities or data services is called compliance. So we have a bunch of compliance workflow keep running, making sure data is in a compliant state. Third one, you may be very familiar with this, compaction. I also have another slide talking about this in the details. Last but not least, we are using Iceberg. So as you may know, Iceberg requires a bunch of maintenance job to making sure Iceberg in a good shape. So that's something that we also orchestrate on behalf of users. Last component, which is not directly owned as part of open house as a product, but I think, which is storage, but I think from users' perspective, storage itself is totally transparent. So I'm just bringing this here. We internally using HDFS as our backend for the storage. Things that open house manage there are data files. We're using org. Also have metadata files. So there's a bunch of Iceberg manifest and snapshot files. It's a recently open sourced project. So if you're interested, please check it out. By the way, if you still remember what Jesus mentioned, the 3-layer things, open house is actually at the catalog layer, but we also manage the second, which is the metadata layer, and the third, the storage layer on behalf of our users. So the specific scale that I'm talking about here is what you can see here in the stats. We just entering production phase maybe 8 months ago, and we have a bunch of Iceberg tables moved into, we have a bunch of Hive tables moving into Iceberg tables as well. So at this point, we're sitting at about 8,000 tables. We're occupying 6 petabytes of the storage. We have 120 million number of objects. So if you do a quick math, you will figure out the average file size is around 50 megabytes, which is not the best thing. So I'm going to talk about this later. Number of jobs that we are managing on behalf of our users is about 22K per day. The last thing that I want to share is I mentioned that we enable table share from a programmatic way. Looks like our user love this feature, so we are recording about 10K plus share requests in a peak level. Talking about this share API a little bit more brings us to the first problem that I want to touch based on our operational experience. So starting from the API, this is really just a SQL standard API that we offer to users so that if you create your table or you're just a privileged user of a table, you can run this grant select to on the table to some other folks around your team or within your team. Implementation of this API consists of two parts. We need to make sure the metadata is properly authorized. That's done by Open House itself. We also need to make sure the data authorization is being done. Basically, what I'm talking about is when you change the permission of your table, these two things needs to be changed. But because we're sitting on top of HDFS, the data authorization part is implemented using HDFS POSIX semantics. Problems of this, we have two places to implement this RBAC or table level RBAC authorization. So sometimes if you're calling one of them successful, the other one fail. So we will have this inconsistency between the two. You can also have some other limitation on the data storage or data authorization process because there's only one account that can be the admin of this path, which means there is only one table admin for that path. So that is really something that we feel restrictive as a feature to offer to user in terms of RBAC. Last, because of some of the scaling constraints that we have, a user can be only a group membership to up to 500 path. So which means if I want to be different, if I want to be more than 500 different tables, I will have some problems. But by the way, this is just constraints that we have. Solutions that we're trying to resolve these problems are actually thinking one step beyond HDFS. Like if in the open source implementation, we can bring this blob storage so that we can authorize the data access using a mechanism like sign URL or token. So that effectively makes Open House as a layer to mint a token for applications so that we can achieve a consistency between the metadata and the data in a single place. And other observation that we have is it's probably the first time that we offer a programmatic way for user at LinkedIn to request share or to share tables with others. So we are seeing a lot of users using this, but we are implementing this feature on top of legacy infra. So that's something that we will need to consider in the future to evolve at the same time. Second categories of the problem that we also observe is within the data service. So again, we passed the API layer, we get into the data service layer, is about open file deletion. So for folks who are not familiar with Iceberg, Iceberg essentially is just a root of metadata. So this root or this tree actually referencing all the files and data files. But sometimes you will have some files or metadata files that are sitting in the storage or the table relevant location, but they're not referenced by this tree. So we call them orphan file. Orphan file deletion is intended to making sure these kind of files are being cleaned on time. But there is a tricky scenario, like if you have a long running transaction, for example, if you're Spark jobs and you dump a lot of data files, your job took like 12 hours. I don't know if it is typical for you guys, but I have seen this kind of things. your files are being written in the place, but your metadata is not being committed. And at the time, before you commit, OFD came into the picture and recognized those things as, orphan files and get rid of them. But when your Spark job commit the metadata file, it's not aware of such things called OFD, and it shouldn't. So it commit the files, and then you lead to a table state that is corrupted. Similar situation happens when application, if they want to manage the commit state themselves, like they have big application, they write a bunch of things, but the commit failed, and they decide, okay, I'm not going to redo this data writing later because I know data were there. I'm going to manage this state myself, and I'll wake up later and I'll just do a commit. And for this kind of example, you will also have running into these similar problems. And ultimately, I think the pattern is, I wrote here, I know the font is a little bit small, but ultimately the pattern is you write the files before you commit it, and at the same time, OFD kicks in and get rid of them. So as a solution, or I would say a workaround, we are extending OFD in a way that we change the way we detect or determine something as orphan files. So for anything that is recently modified, we will waive the orphan file detection to them. And the other thing that we added here is we don't want the orphan files just to go away permanently at the first shot, but we add a stage called staging location. So they are being moved there temporarily, just in case that we falsely detect something as an orphan file, we still have a chance to recover them. Second problem that we see in the data service category is called very similar name, orphan directories. These things is something very interesting that we discover while we are operating this Hive to Iceberg migration. So one tool that we leverage a lot is using this command called ctest. So it basically just say, I want to create an iceberg table, but the source of the data comes from select star from this Hive table. As you can see, this table, this process can be quite lengthy if your Hive table is big enough. So the similar problem will happen, like maybe the service itself has some hiccup or something else happens. So you read a bunch of data, replicate this data into a new location that associates with your new iceberg table, but the commit failed at the last stage. The problem here is it will become a folder that then goes in a storage layer. OFD does not discover them because this path is never being cataloged into OpenHouse. But the prerequisite for OFD to work is it needs to be at least discovered by the catalog layer. So OFD will not find them. Actually, no one will find them if we don't do anything here. But we thought this will be a rare issue initially, but because we are using this process as a migration tool, for the time being, this is actually more prevailing than we expected, and actually poses some storage threats for us as well. Solution here is relatively simple to understand. We just developed something called orphan directory deletion as part of our housekeeping suites. What it does is basically compare the list of the paths on the OpenHouse namespace and compare that with the one that are in the catalog. And I think we also figure out there might be some other use cases for this, like soft delete. You can, so right now, if you drop an OpenHouse table, everything will be gone at the single shot. But sometimes we don't really want that to happen. Maybe user miss a command or misoperate from their SQL shell. So we want this soft delete to be the default behavior so that when you drop, the table is the catalog, but the data is still there. Last category of the problem within data services type is what I call retention on legacy partition schemes. I'm not sure if this is a unique problem for us, but I'll just unpack from here. Our vision, one of our vision is to make table management or data management declarative, as I mentioned earlier. So by that, in the context of managing your tables, TTL, we call this retention API. So we want user not implement their own jobs to manage the life cycle of their table. Specifically, a lot of time partition table, they tend to be, okay, retained for really long, like 5 years, 6 years, but a lot of our users actually don't want that to happen, and they want to save the cost for us as well. So we developed this API for them to declare that, okay, I only want my table to be stayed there for 30 days. And this is a pure metadata API. It does not trigger any data operations synchronously, but the rest of the work is on open house to making sure that this 30 days state is actually being reached. But in reality, we find things are not that straightforward. Like we are seeing this legacy pattern prevailing or very dominant from Hive world, which is you have a partition column in string type, but the value of it is actually carrying some time semantic value. So for example, today is 2024, May 3rd, I believe. The value of it can be just like this string. So the problem for us is we don't really know what does this mean when we try to determine if a partition should be retained or not. So intuitively, what we do is like this complicated API. We want user to tell us not only this retention period, but also which column you want to apply your retention. And the most complicated part is you need to provide us the pattern on how to parse this retention columns value. But this is really error prone, as we observed. The other interesting thing that we discovered is this implementation choice. So if you think about this retention, it's really just a delete your older data, right? There are two ways that I show here. One way is you put the data partition at the right side of the predicate, but you come up with a timestamp object that is that serves as an anchor for the latest time you want to preserve, and anything before that you want to get rid of. So the transformation happens on the right side of the predicate. This one is actually pretty good because this is, as long as you have the left side of the predicate being the partition column, this is a metadata only operation. But what was a little bit surprising to us is if you look at the next one, you apply the transformation on the data partition column itself, but on the right side of a predicate, it's just a timestamp object. And this one actually results in full table scan with the rewrite operations. I believe this is because the predicate is not get down to the lowest level in the planning process. I think it's a resolvable problem, but I'm just bringing this out as it's probably something that we don't anticipate. The way we address this complexity on the API level is we end up doing some survey, trying to figure out what are the patterns out there. And luckily, we find that the dominant pattern is actually YYMMDD or YYMMDDHH, depends on the granularity. So we just make them default pattern. So users don't really need to give us pattern in most of the cases. But of course, if you're an advanced user, you have some interesting pattern that you don't want to move away, you will still need to go with this complicated SQL syntax. And the other thing that we want to talk, or I think what we learned from this is this string-based partition scheme is really just an anti-pattern. But we make the decision to carry this forward because it's really hard for us to change our users' SQL implementation. Basically, they need to rewrite a lot of their things, so we want to avoid that. Last part, we talk about API problems, we talk about data service problem, and the remaining part is storage. So the problem that we observe is really the storage efficiency. So in our context, it translates to the number of objects that we are managing on top of the table. When we migrate a bunch of Hive tables to OpenHouse/Iceberg, we're actually seeing the number of objects that occupied by this migration is growing. The problems of this is kind of classic to HDFS because you have this single point of failure in the name node to scale because of the number of objects to grow. We could try federation, but every time we moving data sets from one cluster to the other clusters, it's pretty labor expensive operations. So we end up with create these things called quota to cap this growth by users, for users. But they, from time to time, because of this growth, they from time to time run into the problem that they need more quota. I think when we dig into it, we figure out that one of the cause is Iceberg itself has some level of right amplification in terms of the number of objects. And what we see here is usually it's around 1.8 to 2 times than the Hive counterpart. I think it's not a very universally generalizable pattern because it really depends on the producing pattern that you have in your tables. Especially if you have a lot of override, you will end up with a lot of overhead on the number of objects. Second part, I probably don't have time to dig into deep here, is a very classic old friends, small file problems. But this time, the relevant part here is it's coming from a Spark jobs that were using file paths as input, and a lot of configuration that they use to control the number of partition at the output is no longer working because you're dealing with a table as an input. So you may think that compaction will come to rescue, but compaction actually itself comes with some overhead. We're seeing compaction generating some overhead in terms of the write throughput. We're also seeing there is a surging in terms of the objects when compaction just run over some tables, which is understandable. The second part of the overhead actually comes from a compute because running compaction is not free. And the way that we model this is the compute resources coming from the user queue instead of that we centralize the management of those compute resources. So all these things really brings us to the problem of the ROI of running compaction. But so far, the way that we operate compaction is we look at some tables and we understand, okay, here's the small file problems. These things really needs to compact. So we manually pick them, but I believe we will need a more systematic way to determine when and what to compact. And this is actually some collaboration that we had with GSL folks on how to determine which table should be the right candidate and when to do that. Okay, future work. I think I talked about scale. I believe our goal here is to scale to 100K tables because we really want to make Open House the de facto offline catalog for all the tabular data sets at LinkedIn Data Lake. Other parts is dynamic layout optimization. As I mentioned, this is a collaboration that we had with GSL team. So far, we are looking at system table, or we are manually pick up some tables to run compaction. But in the future, we probably want to look at the query plan to see, okay, this table, 99% of the query is predicated on this column. So can we do something about this? I believe Shardu, which is our teammate, will talk about this later in his slides. This will be an open source work that we will focusing on making the interface right and allowing different creative way for the decision making. Last but not least, we will also focusing on other OS's components. We recently open sourced, but we will making sure that we work on this easy cloud deployment just to reduce the friction for the new users adoption. I think we also see people asking for Trino integration. We actually have this internally, but we will figure out a way to bring this to the community. Yeah, that's all I have.
All right, thank you, Lei, and thanks to all of our speakers. Now we have one more trivia question coming up. So, which data services help to clean up data files if you do a create table as select and the transaction fails during the final commit step? Is that orphan directory deletion, orphan file deletion, snapshot expiration, or partition expiration? And we have, oh, thank you, a charcuterie board. Okay, did we have a hand? Did you? Can't yell out the answer, get out of here. All right, well, was she our first hand? I wasn't watching. All right, in the corner. There we go. Yes. B? And the answer is A, orphan file, orphan directory deletion. Oh, even I'm struggling. Oh, I wasn't supposed to share this until we got a correct answer. Sumit, can you give me Sumit, can you give me a live trivia question right now to redo? Okay, how many stars do we have on the Open House GitHub repo And I'll give you within 50. Yes. 650, no. 670, no. 600, okay, we're too close together. We gotta spread it out a little. Yes. More 600? 800, no. We got a cheater, but I'll give it to him. We have 247, checking the live data. Great work over there. I appreciate the hustle. Okay, my apologies for being a bad trivia host. Okay, next up. Oh, we have one more trivia question. Sorry, I forgot. Very bad trivia host. So using a single node, how long would it take to convert a full terabyte of TP-CDS dataset, originally produced in the Delta Lake format, into the iceberg format, using Xtable, I assume? A, it will crash, can't be done. B, more than an hour. C, 10 minutes. D, less than a minute. I'm gonna check the answer this time. And yes, D, less than a minute. While it depends on various factors, we have our asterisks here. Typically, the metadata size would be less than 100 megabytes and can be fast. Okay, do we have prize for Abhishek? Oh, we got it. Okay, it's already done. Cool, so next up, oh, sorry. Before we move on, we have some Q&A. So we should have about 5 minutes for any questions. We have a mic in the center. So please go ahead. We're happy to take questions. And yeah, speakers, if you want to come back up. Oh yeah, if you turn it on, sorry.
Hi. This one probably is for Dipankar. When the source and destination table between Xtable are being written to concurrently, how does Xtable handle that transaction? And also, first of all, is it supported? And secondly, is there any transaction guarantees on it?
I think it'll be primarily like right now we aren't like it's more of a like I would say like you would first do it like for the first setup table, but I'm not sure about the concurrent part.
So typically the pattern is that there is one owner of the table. This is how data sharing would work in industry in practice, right? So one owner keeps writing the files, the others are just readers, they're consuming the data. It is possible. Yeah, and it is possible that if there is no coordination service currently implemented with Xtable, so there are two writers, we do not coordinate right other outside what Iceberg or other catalog implementations would provide. So what we currently test with or support is single owner of a table, which is writing the data. In future, we can add more of it.
No, I think that's basically the current use case is mostly read replicas of the original table, and there is an owner for the original one. Yeah.
Got it. Thank you.
And then obviously, you know, the original one kind of gets dictated the guarantees, right, in terms of the original table format and what they offer, right? So yeah.
Thank you. Directional works if you try, but not something we do in practice.
So we heard about Xtable today. I think actually the last data meetup we hosted here, we heard about Delta Uniform, which is doing some similar things, right? Can any of you talk a little about, you know, how you feel about maybe differences between the projects or how you see the two evolving? Is there space for two of these? Should we be consolidating? How do you see that evolving?
I can provide some context. Like uniformat, of course, like the kind of the main differentiation right now is that it's not omnidirectional. It just so how I see it is more of a one-off migration strategy, and it basically like takes one format and translates to other. But it's really hard to like go from the other way around. Whereas Xtable would be more of like the omnidirectional thing. Also from a governance perspective, I'm not sure. Like it's not open source probably. But yeah, that's another part like towards it. But yeah, I'll let that.
I mean, I wanted to comment about the governance. In fact, I think Uniformity is open source. It is under the Delta Lake project. What we wanted to do with Xtable really was creating a kind of share ground for all the different table formats, and it's an independent project. So I want to touch upon that. The governance is probably going to be very different. We're trying to bring, practitioners, users from all of the table formats, and kind of creating that kind of shared project that anyone can participate in. And that's also why it was migrated or donated, to the Apache Software Foundation, and it's under incubation right now. So
I think that those are the two important points of omnidirectionality. From our perspective, we do not really promote a particular table format, right? We want to support all table formats, interoperability across engines, table formats, storage layers, and having that omnidirectionality and a good governance model behind it is something which is extremely important for us.
Okay, we have a question online. It's from Chris. He says, thanks for a great talk. In the Xtable demo, it looked like you refreshed the S3 bucket and showed that there were new translated metadata files in a different format than the original table format. Does the Xtable materialize translated metadata, or does it do the translation on the fly every time a client accesses the table? And if it does do the materialization, how do you keep the files with different formats in sync when doing table maintenance?
Yeah, I'm not sure about the table maintenance part or even the materialization part, but what I think is personally like working like with the project itself. I feel it's like a on-the-fly translation, right? And it's basically like putting the metadata from one format to another. But is that like there is a materialization? I don't think so. Or do we have any materialization?
So I think the question was that when a read query arrives, at that time, do we generate an in-memory data or not, if I understand the question correctly? So we don't. What currently Xtable requires is it is triggered externally. There is like, if suppose a new file is added to the file system, then we can listen to change data events. And based on that, so this could be triggered, or it could be manually triggered, because if it is too expensive to create too many copies of all the transactions on the target side. So it's a library. Most common pattern is that it's invoked periodically or based on an event. Like it could be hooked to any of the engines when the commit happens on, say, Spark or say Flink. At that time, Xtable is triggered for that particular transaction. So it's not based on read, it's more based on the writes which happen on the file system. All right. Thank you, everyone.
Thank you again. Cool. And so next up, we're going to have Sherdul. Sherdul is a staff engineer at LinkedIn. Has deep experience across the big data SQL ecosystem specifically, including extensive work on Coral, LinkedIn's open source SQL transpiler, and now focuses on Spark's SQL engine. So Sherdul, please take it away. Oops.
Can you guys hear me? Okay, great. Yeah, all good. Cool. Good afternoon, everyone. I'll be talking about how we collect and analyze rich Spark SQL plans here at LinkedIn. So let's first look at what a SQL plan really is. So when you submit a query to Spark, right, there are various stages of processing that happen. The first one is the parsing, where you go from your plain text query string to tokens. Then there's the analysis phase, where tokens are resolved. For example, if there's a table name or a function name, those are resolved. There are some type validation, type checks that happen. There's the optimization phase, where the optimizer will try to improve the query structure, in hopes of better performance. And lastly, there is the planner, which creates an execution plan. And that defines really how the query is run. Now, throughout this whole life cycle, Spark operates on a tree-like data structure that's called the query plan or the SQL plan. So it's really like a graph data structure. And this process is similar in other database engines as well, even in traditional relational databases. And so what happens is you get this graph, which represents the flow of data within your single Spark query, right? So you start from input data sets. Those are the leaf nodes in this graph. It's probably a little bit too small to see, but you can kind of see the structure here. There's two input data sets, they're being joined together, and then there's an output data set. And so you start with leaf nodes, which are inputs. You go through all the relational operations, such as joins, filters, projects, aggregates. And then you finally end up with the output data set. And now, if you are familiar with Spark and debugging Spark, you've probably seen this image in the Spark UI, when debugging your SQL queries. That is the SQL plan for your query, right? And it not just provides us with the flow of data, but it also provides much more information. In the UI, if you move your mouse over one of these nodes, you'll see more information. For example, for a join, you can see the column or the join key. For the input tables, you'll see all the data types that are coming from the input table. So it has lots of information about the query as a whole. Now, to give a sense of why we are interested in these plans, let's look at the scale of Spark at LinkedIn. So Spark runs on Yarn clusters at LinkedIn. We have a couple of clusters totaling to about 40,000 nodes. And we have about 300,000 daily applications with over 3 million queries. And yearly, we've been seeing about a 3x growth in Spark applications. Now, while the Spark UI is useful for one-off debugging, and that's something we use very heavily when we are working with users in office hours dealing with issues. We really wanted to understand what happens in our cluster as a whole, and that's why we started looking at these SQL plans. Right? So these plans really help us understand user operations without having to read through their source code, the application source code. And this is especially helpful for data frame applications, which are authored using Java, Scala, very complex code, lots of files, sharing functions between themselves. Okay. And since in Spark, the data frame API is also backed by Spark SQL Catalyst layer, these plans are available for both data frame applications as well as applications authored in pure SQL. And so these plans are much more friendly to machine parsing than Java or Scala source code. And even though parsing SQL source code is easier, you get a lot more richer information, like I said, like columns, data types, and everything from the SQL plans. And these files, these plans also include runtime metrics. So, for example, the number of rows passing through your filter operator, or the time spent planning a particular table scan. So it gives a lot of operational metrics for us as well. Now, because of these plans, we were able to gather a lot of distinct information about the query without having to individually instrument each and everything and individually collect information. And that all of these properties really help unlock the potential to perform cluster-wide analysis of Spark jobs. Now, we are using these plans for a few things. Firstly, when we are making improvements to the Spark engine, we use these plans to validate our hypothesis. Is this improvement going to be useful for us? And we have lots of data about our production workloads. We have collected these plans over a few months or so. And so we can better quantify the impact of these changes to our, does it matter for our customers? Right? And that's what we really focus on. We, if your change really changes the query shape in any way, these plans become a key metric to monitor during rollout. How many queries are operating with the previous optimization versus the next optimization, the new optimization, and so on. It also enables us to give workflow specific recommendations. For example, suggesting better config values or code changes to our users. And I think until this point, we were really focused on application level insights, things like how much memory your application uses and what should the right memory config be. But with these plans, we were able to dive deeper within an application. We can look at a single SQL query and suggest changes based on that. Lastly, we also use these plans for auditing. So we audit user operations and user behaviors. And we'll see concrete examples about all of these a bit later. But first, let's look at the process of how we collect and store these plans. Now, these plans or the representation of these SQL plans already exists upstream, right? If you must have seen this if you ever run the explain command in Spark, you've probably seen an output like this before, and that's how it's represented in open source. These plans are captured during query submission, and they are available through the Spark history server or even the Spark Live UI REST APIs, right? And this is largely what we had been using previously for cluster-wide analysis. However, there are a few key issues with this representation. Firstly, you can see it's like there's some basic formatting in there. There's some indentation in there that's useful, but for the most part, parsing it required lots of complicated regexes, and that gets messy very quickly, right? These plans also do get very large, right? And so Spark had put limits everywhere. So if you see, I've highlighted a couple of cases where the columns that were printed were truncated. So we only see the first few columns, even the filter string has been truncated. So we only get a partial view of the query. And to some extent, this was driven because of how these plans are implemented in Spark, right? So when you do an explain command, it generates one large string in memory. And so for large plans, like this sort of pattern causes a lot of a huge string to be built in memory. And we've seen cases where applications actually run out of memory just to explain the SQL plan, right? And if you've seen newer Spark versions, they have a slightly better formatting than what we've seen there, but the issues that I've mentioned largely still apply to this representation. Just a quick detour into why we see large SQL plans, because you may be wondering, SQL files are probably hundreds of lines of code, maybe thousands. Why such large SQL plans? We see that they typically come from Spark Dataframe API usage. And in some cases, we've seen in the order of hundreds of megabytes or even gigabytes of plan sizes, right? And an obvious example of that is very wide tables, ML feature tables, for example, thousands or even tens of thousands of columns wide. But we've also seen some suboptimal user patterns. One example is we had a platform built on top of Spark, which generated wide tables, but the way it did it was it created one column at a time. So it did dataframe.with column A, .with column B, with column C, and so on. And so it generated thousands of project nodes. Now, those project nodes do get merged together in the optimizer. So it doesn't really affect query execution. The execution is just fine. It runs just fine. But in the plan, it still shows up as lots of project nodes. There were also cases where users were passing large literals, such as sets, as UDF arguments, and those sets would get printed in the SQL plan. So because of all of these issues, we decided to look at better ways to represent the SQL plans. And we came up with a more structured representation. Now, the representation that you see on the right is sort of a JSON representation, right? So it's actually the pre-order traversal of a plan. And we output a flattened JSON array. So each operator in the original query, it's a JSON object. So for example, an operator like a join is one object within the JSON array. And the attributes of the operator, for example, the join type or the join keys, those are object properties. Now, there's lots of information about every operator in here, but to be concise, I've just removed most of it. I've kept the most important points, but there's lots of information in there. And this does generate a lot of output. But one thing that we've seen was these are highly compressible strings. So the on-disk size was less than 1% of what the in-memory size was to generate these plans. So they are really good to compress. We use the standard compression, and that helps a lot. Right? But throughout this, our intent was to preserve as much information as we can, so that we can come back and analyze Spark jobs later. They also include runtime metrics that you can see. And so this is sort of a semi-structured representation. It's not fully structured. It's not like there's no schema for it exactly, but it's not as bad as the previous one where we had to do regex parsing. And this does exist in open source actually. There is code to generate a JSON representation like this. It's just not used. It's just a function call which no one makes. And so we largely use the same thing. We made some modifications to it. The first thing is we don't build this huge string in memory anymore. We write it out to an output stream so that it's flushed out at regular intervals. And secondly, we made some small changes. For example, how arrays are serialized was a bit different. In open source, it was just like a comma separated string. It just merged arrays together. So we changed a few things here and there, but largely it's what exists upstream. How we collect them? So in the Spark driver, we have a small Spark listener, which listens to query completion events. And after the query completes, it collects a few plans from it. So the parsed plan, the analyzed, the optimized, and the physical plan. Different plans are useful for different purposes. So the analyzed plan is much closer to how the user has written the query versus the executed plan or the physical plan is much closer to how Spark runs it. So they are useful for different purposes. Now we write this out to a SQL plan file on HDFS. And finally, we have a batch job which collects all of the files from different Spark applications and stores it in a SQL dataset for further consumption. We also wrote a small Java library to just read from this table, and we have a visitor sort of pattern which we use to analyze these plans and go through them, extract information that we need. So let's look at how we've really put these plans to use at LinkedIn. The first one is identifying caching opportunities. So Spark does lazy evaluation, right? So you have a query, you have like two tables, you're reading it, joining it, filter, blah, blah, blah. When you're writing this query, Spark is just building like a DAG of operations, like a query plan where it's representing your transformation. It doesn't really execute anything immediately, right? Until you run an action. An action is writing to an output data set or collecting like the number of rows that are in the data set. So something in which an output is returned back to the user. And to keep queries maintainable, users typically, what they do is they create lots of temporary views which represent intermediate data sets. And then they use those intermediate data sets, temporary views, in other queries. A common trap in all of this is users don't realize that it's a temporary view, it's not a materialized table, which means when it's being reused in multiple queries, the whole computation is going to rerun, right? And Spark does offer a feature to combat this called caching. But in this case, the user has to deliberately write the cache command, right? The user has to first understand that this is happening and know that there is a solution to it and use it. Okay? So many users often miss this. And that's why we wanted to see if there's evidence of repeated computation happening in our ecosystem. So what we did was we calculated a hash value for each operator in the plan, right? So the hash value depends on the operator name, for example, join, the parameters, for example, join keys, and the hash value of all its children, right? And so in this example, you see there's two tables being read and joined. The first three nodes in both queries have the same hash value because they're exactly the same nodes. And then the last one, the hash values are different because the filter is slightly different. One filters on US versus one filters on India. And Spark actually already offers a better version of this called a semantic hash. And in this example, you'll see that the semantic hash for both the queries is exactly the same, even though in the filter node, the order of operations is reversed. And if you see the left one has greater than, right one has less than, but it's still semantically the same, filter condition. So semantic hash handles some cosmetic differences for us, like commutative and associative operations, or cases where sets are involved, but the order of elements within the sets is different. So what we do is, we gather the semantic hash for all the operators within, all our SQL query plans. And if we find two nodes which have the same semantic hash within the application, we can be confident that it's exactly the same computation and it's a candidate for caching. Okay. So we ran this analysis over a week in our ecosystem. We found about 10,000 caching candidates. Right now, not all of these are useful to cache. There's always a trade-off between memory, how much memory is required to store the data set versus what's the cost of recomputing the whole repeated computation. So we had some reasonable thresholds that we set on both of these parameters. We know the approximate size of intermediate data set from the runtime metrics that I've mentioned. Same thing for the cost of recomputing. We know the approximate time it takes to recompute the data set. So we set some reasonable thresholds on it, and we found a good list of candidates and we worked with those users to implement caching in their applications. In the largest instance, we found, there was a platform built on Spark which ran thousands of jobs in a day, and each of those jobs had this common pattern of caching. They were reusing some data sets, and with that fix, it was actually a one-line change. With that fix, we saved about 1 petabyte hours of resources per day, and that was a big win for us. And it was we could not have really figured this out without the SQL plans work, because the platform was built using Java and Scala code, and the code was a bit messy, and the place where the data was generated versus where it was reused was actually 2 or 3 layers of indirection, deep. So the plans were really helpful in all of this. Another use case was join tuning. So Spark has multiple implementations of join, right? Hash join, a broadcast join, nested loop join. It tries to use broadcast join if one of the datasets can fit in memory, and by default, the 10 MB is like the Spark default config for broadcast joins. We wanted to see if we can come up with a better threshold that matches our workloads. And so we ran an analysis which gathered the distribution of data sizes for join inputs. And we saw that 60% of our joins had one input less than 30 MB, right? So just by increasing the broadcast join threshold from 10 MB to 30 MB, we actually doubled the amount of broadcast joins happening. We also did some analysis to make sure that when we increase this limit, it does not cause a significant increase in memory, because that's the trade-off, right? Broadcast joins would use more memory on each executor. So we did some analysis to make sure it would not cause a lot of jobs to fail. And as a result, we rolled out this increase. Lastly, auditing. So we have some internal use case that require that a table not be accessed directly, but rather on views on top of that table. And those views do perform some data cleaning and data transformation. So we use these plans to build sort of a lineage, a mini version of a lineage to make sure there were no cases where the table was accessed directly. And I think generally we've been using this to answer questions like how many Scala, Java UDFs are used, how many queries they are used in, what are the most common DDL commands. So just general workload insights. So that mostly wraps up what we have been working on. We are also exploring some future use cases. As Lei mentioned, dataset access patterns can guide storage optimizations. So if you have a range query on a column, it's better for that column to be sorted or data to be sorted on that column. If you have a column which is used in joins a lot, maybe bucket on that, right? So we are trying to analyze our query plans to see what's the usage pattern like. And secondly, I didn't know Lei was going to bring this up, but I had also been looking at predicates and like cases where predicates are not pushed down to the file format. And that causes large table scans, right? And that's because there are some complex predicates. There are UDFs being used in those predicates, which Spark cannot really push down, right? And so, yeah, we hope that using these SQL plans, we can improve the efficiency and performance of our Spark jobs. Yep, that's mostly what I had. Thank you.
All right, thank you, Shardul.
Yep.
We'll see if I can do a better job with trivia this time. And where Okay, our prize is coming up now. So let's see what we're playing for this time. We have a water bottle. I have one of these. They're amazing. It's insulated. It has the straw. Great water bottle. Highly recommend. Okay, so what is used to detect equality between two subplans of a Spark query? Is that, all right, I'm not gonna read the answers. I think I saw no repeat winners. So I think I saw maybe that hand first. Go ahead. Semantic hash, drum roll. Semantic hash, that's correct. Congratulations to our winner. And now before we go on to Q&A, we're gonna have a brief message from our sponsors, the LinkedIn talent acquisition team. So take it away, Matt.
Thank you, Eric. And hello, everyone. Thank you for coming to LinkedIn today. If you are interested in learning more about opportunities working here at LinkedIn on all this awesome infrastructure you've been hearing about today, come find me and I'll help you get learn more about the opportunities here at LinkedIn. So I'll be out front, and then during networking, I'll be over that table there. So happy to chat more. All right. Thank you so much.
All right, thanks, Matt. And with that, let's go ahead and open it up for questions. Mike is available. If you don't mind using the mic just so everybody can hear, okay? Thank you. And we might need to turn it on.
How much was the cost saving from the reduction?
I think.
Oh, sorry. Yeah.
So, I'm not so sure. I think so I was just looking up like how much AWS EMR, for example, costs for the same thing. So exclusively based on AWS costs per GBR, I think it was about I think it was like $1,500 per hour, and so that would be probably like, I think it was like $500K per year or something. That was just from that single application where we implemented caching, right? And we did it for like about 5 or 6 of them. And we're also working to democratize that data sort of. So we have a portal where we show insights to our users about an application. So we're trying to integrate these insights in there. So yeah, from that one instance, about 500K, but that was also the biggest instance. And yeah, the costs are AWS costs, not LinkedIn costs. Yeah.
And from the broadcast join?
That I think was a bit harder to compute, so I don't have an answer for that. Yeah.
Thank you.
Yep.
Okay, nothing else then. Oh, we have one more. Okay, go ahead.
I would just be curious, how do you see different evolutions in Spark use cases across the company if you actually have analyzed all the query plans versus maybe also what you're seeing for warehouse access queries?
Okay, can you repeat the question?
Yeah, so just what kind of workloads are you seeing from Spark? Are there a lot of application workloads? Are they just like batch jobs? Are you guys using a lot of ETL? Like what sort of workloads have you been seeing?
Right. Yeah, I think it's mostly been batch jobs. We also have Trino at LinkedIn, which caters to really the ad hoc interactive style of usage. We have Samza and Flink, which looks at like nearline, or I think more of the online side of things, streaming side of things, right? So yeah, for Spark, I think we are mostly focused on batch jobs here. And I think lots of ETL, machine learning, and that sort of standard Spark workloads, but not so much on streaming. I think we recommend Samza and Flink and other systems. Yeah.
Thanks. Yeah.
Okay, we have time for one more if there's anything else. Good.
So you mentioned that you learned about other kind of Spark job optimization opportunities, not at application level, more at query level. Could you share some details on what findings were like at query level, other than that broadcast stuff?
Right. Yeah. So I think the examples, like the caching example, for example, that was one. Secondly, like cases where predicate pushdown isn't happening. So we could suggest users saying, hey, don't use a UDF in your partition predicate, that you have. So things like that, where it's not like for the whole application, but for a specific node within a specific node. So yeah, that was mostly.
But not in terms of like memory usage or actual tunings of the job.
Okay. Yeah. Nothing that we have worked on right now, but we do have those runtime metrics, right, which are useful. So yeah, the joint tuning was one of those, but that was at a more global level. We just increased the global threshold. Yeah, we do have those, but I think nothing that we've worked on already.
On memory tuning, we actually have a separate work stream, which you will likely be hearing about in a future session, so stay tuned. Okay, thank you, Shardul. And please thank our speaker again. And next up, we're going to be hearing about ViewShift, hassle-free dynamic policy enforcement for every data lake. So we're going to have two speakers here from LinkedIn. First up is Wala Eldin Mustafa. He's a senior staff software engineer in LinkedIn's data infrastructure org, focused on building technology that bridges various big data compute platforms, data representations, and languages, and has had work featured in conferences including VLDB, SIGMOD, ICDE, as well as IEEE Big Data. And he'll be joined by Kai Tran, also a senior staff software engineer from our privacy infra org. And Kai focuses on data governance and has worked on big data in a variety of capacities, including at Oracle Labs, AWS, and Airbnb, as well as, of course, LinkedIn. So please welcome our next speakers to the stage.
Cool. So, all right. Wait. Okay. So let's see. How many of you have had to deal with compliance before, either through enforcing it or through adhering to compliance rules? Okay. Looks like a good amount of you. So more likely than not, you have had days where you felt like our friend here, the staff engineer, who's very overwhelmed with the terms that he keeps hearing about compliance, such as GDPR, CCPA, DMA, PII, right to be forgotten, and privacy by design, and so many of those buzzwords. On the other side, he's very responsible for managing a very large data lake with a vast number of applications, and he just wants everything to work. This sounds like a very big challenging problem indeed. And at the same time, privacy by design is on the rise. So companies who manage user data are implementing ways to put the users in the driver's seat to have good control over their security and privacy effectively. So these platforms provide tools such as privacy dashboards and options to export user data, either to keep it for the records or use it in external services. And they also provide ways to tune the ad preferences, so the user can control what type of data can be used in displaying ads to them, in addition to providing ways to perform regular security checkups and options to even delete the data completely from the site. So although managing compliance might sound overwhelming, the solution is surprisingly simple. So to handle compliance, you need two key platforms. One is the policy engine, and the other is the query engine. So let's see how this works. So initially, policies are inferred from regulations and internal company guidelines, and then encoded in a structured format that is kept in a policy store. And that is fed to the policy engine along with the data lake metadata, which is comprised of the table schemas and the column annotations denoting what type of business use case they are used for. And then that policy engine produces a set of SQL views that basically encode the transformations that are required on those data lake data according to the usage in the specific compliance use case. Those views are subsequently then fed through a query engine along with the data and the applications. And the output of that is data compliant applications that run in the data lake. So with that, we've gone from a complex maze of policies and large number of tables in the data lake into a clear path towards compliance. But wait a moment, like, why did we choose views? So views actually have a set of interesting properties that makes them very good candidate for use in privacy and security applications. So first, they are expressive. Basically, they can express a variety of use cases for compliance using tools such as projections, filters, joins, and UDFs. They are also portable, so views can run on multiple engines thanks to the nature of SQL, which is standard for the most part. And they are also modular, meaning that they can be drop-in replacements for the base data, where they can kick in and start filtering data from the underlying tables virtually. They are also agile, meaning that they allow us to roll out new versions of the obfuscation or like policy logic, or roll back to previous versions in case we want to fix bugs. So let's take a peek at some of the ways views can be used in privacy applications. So for example, one way to use views is to leverage column level filtering, where basically like an entire column can be stripped away from a data set, and then the consumer of that data set is not even aware of the existence of that column. Another way is to perform column level masking, where the column still exists, but the values are obfuscated, where the underlying data is not even visible. A third way is to do row level filtering, where we can use filters or where clauses to filter out rows that shouldn't make it to the result. Even more complex, cell level masking, where we can obfuscate like certain data points based on the row value, whether let's say that's a member or a user who's interested or not in opting into a feature, along with the column where that column expresses like a specific data domain or a use case. And even further, these diverse masking capabilities are not restricted to only one type of application. So one single data set can have multiple types of maskings and multiple ways of applying transformations through a series of views that all correspond to that table. And each of them encodes like a unique logic that is triggered in a specific security or a compliance application. So let's go also to the other feature of views, which is portability. So the nice thing about views is that they are metadata objects for the most part, and then you can store them in your metadata store. So traditionally, we've always heard about the Hive meta store as the de facto engine or the de facto meta store for storing tables and views. But Iceberg is also emerging, and there is recent support for storing views in Iceberg. Then by that, we can have our views stored in either representation. And at the same time, those metadata stores are leveraged through multiple engines such as Spark, Hive, Flink, and Trino, and so on. So with this in place, we can have those views persisted in the meta store, but then leveraged in multiple engines. With the caveat that although you might have your views stored in one dialect, you might have to execute them in multiple engines, and those engines might have multiple dialects that they understand. So the good news is that there's even a solution for that. And for this, at LinkedIn, for example, we use Coral, which is an open source library and engine for converting SQL from one dialect to another. So that way we can have our SQL stored in the metadata store in one representation, but then effortlessly run it on any engine on the other side. So let's bring everything together. So this is our metadata store, which contains a set of tables, let's say in this diagram from T1 to T5. And then through the policy engine, we create a number of views, each corresponding to a table. And in this case, each table, for simplicity, has 3 use cases where the table can participate in. Each has a corresponding view. For example, T1, UC1, up to T1, UC3, corresponding to T1. And each of those views would have its unique SQL logic that expresses what has to be done on the underlying data once it is filtered. So this is an example of a query or a transformation logic that would combine the user's data with their settings data, join them together, and then filter out rows based on what the user wants to show or not. So now that we have got an idea about like why views are a good choice, the next natural question is like, how do we roll out views in order to achieve compliance? So one way is the brute force way, which is having the data application owners go literally to their scripts, find every reference of a table, then ask the compliance team, what should I use in place of that table, and then substitute the table name with the respective view name. And then have their teammates review that code, merge it, and then have the engine run. However, do we really want to do that? I don't think so. So this would turn out to be a large-scale migration which is expensive and slow, and also error-prone since it's a human-driven process. Another major drawback of this approach is that it exposes context-specific view information or like use case information in the view name. So that dilutes the business meaning of the table that the users were originally used to, making like the code even hard to understand or read. And another drawback is it's hard to evolve, given that now we want to maybe apply new policies in the future, then we'll go back, do another migration, maybe use new names, and the table names get diluted even further. And with that, version management becomes even harder. It's very hard to roll forward and roll back as well. So can we do better? Yes, we can. So this is where an architecture that we refer to as ViewShift comes into play, where the idea is that we can keep the user scripts intact, no change there, but then change everything during the runtime environment. So let's take an example of this Spark Scala script where it has references to table names. We can see that Spark as an engine runs on the right-hand side of the screen. And Spark, when it parses the script and starts to execute it, it would have to resolve things like T1 or table names. And for that, it would consult a catalog, which we call here the table and view catalog. And that catalog is responsible for returning the resolution for that T1. What does T1 mean? So in this case, we interject the execution and say, hey, T1 is not actually a table, it's a view, and that view name is T1 underscore UCT1. So with that, even though the script is written in such a way, in the background, it is executed as if it was written with views in the first place. So the nice thing and the value of this approach is that it's not only restricted to one architecture or one engine or one query language. You can use it across Spark Scala, Spark SQL, Trino SQL. You can use it across multiple engines, such as Trino, Flink, and Spark, because all of them share this principle. And then you can customize like the integration according to the respective engine architecture. So to summarize, the overarching benefits of ViewShift is that you can roll it out transparently. It keeps familiar table names in the scripts so users are not confused. It is easy to evolve to add a new regulation or have version management on top of the views by rolling new versions or rolling back. So let's take a look at the architecture. So before jumping into the ViewShift architecture itself, let's take an idea about the engine architecture without ViewShift. So a typical query engine would be represented by the blue box here. And that engine would connect to a table and view plugin, whose responsibility is resolving table identifiers and view identifiers. And in a typical use case, the query engine would request from the table and view plugin resolving a table identifier, which then is typically resolved into a table object, and a view identifier that's typically resolved into a view object. So to achieve ViewShift and privacy by default, that plugin is extended with another plugin that is kind of integrated inside the view tables and view plugin, and whose responsibility is to map the table identifier to the respective view that is required for compliance. And that happens through the passing both parameters of the table identifier and the context map. And context map here refers to information about the use case, like what is the purpose of the current compliance and any other parameters that would adjust which view should be selected for this kind of job. So given those two information, the ViewShift plugin converts this information into the respective view identifier that should kick in, and then pass it back to the table and view plugin, which in turn creates a view object out of it and then passes it to the engine. So from the engine point of view, engine initially passed the table identifier, but then receives a view object. And it's worth noting that context map here can be typically set through the engine session configuration, which then is automatically converted to a map that is passed to the ViewShift plugin. So putting everything together, we see like APIs that are relevant to the table and view plugin, and these are standard APIs. You can find them in any open source engine, and then APIs that are relevant to the ViewShift. And this way, we kind of separated between the responsibility of the tables and view plugin and the ViewShift plugin. Indeed, you can have multiple ViewShift plugins living in your single table and view plugin, and then each can be responsible of resolving some use case or some compliance domain. So with summarizing ViewShift and the architecture, now I hand over the presentation to Kai, who has just built an end-to-end use case at LinkedIn for a compliance project using ViewShift. Kai, over to you.
So thank you, Kuala. Good afternoon, everyone. I'm Kai. I'm from Privacy Infra org, and our job is to build the privacy enforcement system. And thanks to ViewShift, it makes our job a lot easier. And I can say that ViewShift is a very nice abstraction. I will show how in the next few minutes. But now let's get back to the engine we built. So let's recall like, the two engines that what I mentioned. We have a policy engine and we have a query engine. And the interface between two engines is a view SQL. So sorry. Here we go. So here we go, that is a privacy view. Technically, privacy view is a SQL representation of applicable policy on a table for a given business purpose. So we will get like a privacy view on a table for each business purpose. And the applicable policy here is selected from a set of data policy. And how do we know that which policy we select for a table? We need additional information from a table called data labels. More like a data label, like how we annotate each field of the table. We assign the semantic label for each field, and from that we know which policy is applicable on the table. And after we can produce the privacy view from policy. Each of the business application now need to access the data not to the raw table data, but through the privacy views. And let me show like a concrete example like how it thing work in the query engine. So okay, let's say that we have a Spark engine with two simple tables, like one table for member demographic and one member for the preference, like a member set on LinkedIn homepage. And so let's say that in that toy sample, we only have two rows, like each row represents one LinkedIn member. And let's say we have an application from LinkedIn Learning that issues like a very simple query, select two columns from the demographic table, and we get the result as expected. Yeah, so far so good. And now like the interesting thing here, we have a second application coming from LinkedIn Ads, and it issues the same query. But you see here now, we get a different result. And you see like the yearboard column of member number one is now. So same query, but you see result different. It's just like a bug in Spark. Very unlikely, right? It's very simple queries cannot be a bug. But what is the difference here? So the difference here, you see the small like yellow text here. We have a SQL that ViewShift.enable equals true. that we trigger the ViewShift, and with the ViewShift, like we run the same query from different applications, we can get a different result. So that sounds similar. Like remember, like same function call, different context, we get a different result. So these are like the polymorphism principle in the object-oriented programming. And actually, like if you guys pay attention, like we are not only polymorphism, but we also use other principle from OOP here. That is encapsulation. So I mean by that, like we treat the raw table data is a private data, and business application cannot access the private data. It needs to access the table data through a public interface we call privacy view. So privacy view are like a public interface. So for business application to access the table data. But let's say I go more behind the scene. Let's get back to our example. So we have a same query run by two different applications and get two different results. And how does that happen? So remember, like what I mentioned, we have a ViewShift plugin. We intercept the Spark catalog with ViewShift plugin, and from that we route the table access to the different views. Here we have two different privacy views, one for learning and one for ads. And the question here is, we have a different view here, but how do we know which views can be used for which application? And the answer for that is from the how we implement ViewShift. So let's say that we had a scene, we maintain a table called view mapping table that map each table and the purpose to a view name. And so so the question here is where purpose come from? So the purpose, and we get a purpose here, like we get a purpose from the application identity. So that is an account we run the application. So like each of the purpose we assign, each of the identity, each of an account we assign a purpose, and then from application we get the identity. From identity we get the purpose, and then purpose combined with table we get the right view name, and then so we access now directly to the right view privacy view. So let's go to the get back to the policy engine. So for policy engine, the input applied is we have two input. First from data policy, and the second from data label. And the output of that is a view SQL. And we have two main modules here: policy matching and SQL combination. I'm not going into the detail, implementation detail of those two modules because of time limit. So I just want to show how those modules work through our running example. So let's get back to our example here. Yeah. First, we have a data label. We have two inputs. First input is data label. Data label is like we assign a label to each of the field and column of the table here. And on the other input, we have a set of policy. So each policy object have three components: the purpose, the label, and then the rule. The label here is the same as label we assign in the data label. And the rule here, we have like a condition and action. If condition true, we take the action, and else we take the other action. And because we have same label here, we can match the data with the policy by the same label. So we just join two tables here, and we open what we call the matching table, the ultimate result, the matching table that lists all of the policy applicable for data set. And the second step, we compile from the matching policy into SQL. And you see here we have two views. The second view, no matching, and we just very simple, select star SQL. But the first view, the S view here, we have matching policy, and we build SQL from that. So let's say how we map from policy to SQL, and we map the if statement in policy here into the case statement. For the condition here, we map that condition into UDF, go ahead member consent, provide the consent name, which is in the if condition there, and then the member ID, it return true if we give member with consent for otherwise. And the action here, we keep the same column. erase, we return null. Let's talk more about that UDF. So that UDF here, technically it's a join. We join with the member preference to get the member consent. But in operation, we see the join is too extensive. So we do that by we compute a bitmap for all members who give us the consent on the given consent name. And in other runtime, we just load bitmap in the memory. So that's in memory lookup super fast. So let's say that how we operate privacy view in production. We have two phases. We have two steps. First, we do view delivery, and the second, we do view consumption. For view delivery, we have a job, the pipeline run every hour to create an updated view. And we have a maintain 10,000 views for in the pipeline. And the view version, because the view keep update, we have different versions for user to choose. On the consumption side, we want to make the migration experience seamless as possible for user. So thanks to the ViewShift, the magic of ViewShift, and also like we give the view schema preserving. That means existing application code work with old table schema, still working with the view because they have the same schema. And then the magic of the ViewShift happen like the routing from table to the view. So no code change required for migration to our privacy view. And we have the bitmap to minimize the computation overhead. So overall, like the experience is like a seamless. User may not even aware that we migrate from table access to the view. And finally, we have a system to audit everything, make sure like user doing everything correct. Any evaluation, we get that and report to make user to fix that. So that is how our system working end to end. And that concludes my talk. Thank you. And that, yeah.
Okay, thank you, Kai and Walla. So we have another round of trivia coming up. And next up, we have coming to the stage a LinkedIn beach towel, I think. Yes. So what describes the relationship between the ViewShift plugin and the Tables and Views plugin in the enhanced architecture? Yes, go ahead. Sorry? Nested? And the answer is D, nested. Great work. Okay, and with that, let's go ahead and open it up for questions. As usual, we have the mic in the center. And if you don't mind turning it on, thank you.
Hello, it's already on. Great presentation. One question is, I know that these policies sometimes are geographically dependent, and so one policy might apply in one geography, whereas not in another. I saw the table and I didn't see a context captured. So is there a case where, let's say, ads is allowed to access age in a certain geography or using a certain policy? How does that routing happen? Do we just use the most conservative policy, or is there a specific routing for it?
Yeah, so that what I presented in the slide. So like how we figure out the privacy view for each of the application, right?
Correct.
So from application, we know the account to run the application. And from account, we map the account to the purpose. And the table and purpose combined, we map that into the view. So that the view encode all the policy needed to enforce the application. Yeah.
Got it. So just a follow up to that is, can one use case have only one purpose, or can they have multiple?
Only one purpose per use case, one purpose per account.
No. Okay.
Because that per account is run by like a different business org, so it should be have one purpose.
Okay.
Yeah, I can add to your question as well. So that can actually also be encoded in the view logic. So if you take a look at one of the view definitions that we had in one of the slides, it can actually capture that kind of business logic. So you can see here that there is like a case when, and here we have a predicate where the user has allowed the filtering or not. You can always prepend that with another condition on their geographic location. so that when the user in a specific geo, then the filtering could happen or not. So it could happen also at the user basis as well by just modifying the view logic itself.
Got it.
Yeah.
Thank you.
Hi. At the very beginning, you said that one of the compliance use cases would be the right to be forgotten. And I was wondering, if you filter out some entries on a, let's say, view level, how do you ensure that people don't get unforgotten in production? Because, well, that could lead to potential problems. And I'm wondering, is the right to being forgotten like also one of the use cases that you solely use this view-based filtering for, or is there a separate logic that kind of makes sure that this data eventually gets dropped from the big data database?
Right. So this kind of architecture is specific to read side filtering, and right to be forgotten is completely separate code path or like completely separate architecture. So yeah.
Right. Thanks.
Yeah.
Right, voila. Thanks for the presentation. So I have one question, like when it comes to implementation of these views, eventually you will leak the file path to the executor, right? So the data in the file is not obfuscated, the columns are there, the rows are there. So the user, if the user has a token to read the file because of the view, then the user could potentially get access to the data, right?
Right. So like again, policy enforcement here is not like solving a security problem in that sense, where like you need to like completely prevent the process from having the bytes in memory and so on. It's more about like the application doing the right thing and honoring what the end user does. But it's not like combating like malicious attack or something like that. Yeah.
Thanks.
So if I understand correctly, basically there is a module in Spark, right?
Sorry?
So if I understand correctly, there is a module that returns the view name based on the purpose, right? So
Module?
my question is, if there is another different type of query engine like your Trine or something else, how can it work? So basically this is only for Spark, or there is another kind of module that can also support other type of query engine as well?
Right. So that part is related to like the separation of responsibility that we've presented in one of the slides. And so here, basically, this allows us to have this architecture be repeatable and reproducible in multiple engines, where the engine would, of course, be the blue part. So that would be Spark or Trino, for example, in your question. And then both of them would have their own plugin layer. This is the part that is changing per engine. And it's kind of blue code that connects this to the ViewShift plugin. Again, ViewShift plugin is independent and can be reused across multiple engines. So you need to implement the green part once, but the red part, which is blue code, has to be repeated across every engine. Yeah.
Okay, that's all the time for questions we have. Thank you so much, Walla and Kai.
Thank you.
Okay, and next up we'll be welcoming our last, but of course not least, speaker, Jay Chia from Eventual, who will be presenting on big data and Python, big data in Python using Daft Dataframes. Jay is a co-founder of Eventual and one of the primary contributors to the Daft open source project, with a history of building large-scale ML data systems, including working on self-driving cars at Lyft. So please take it away, Jay.
Thank you. Yeah, hi everyone. So my name is Jay. I am here today to talk to you about big data in Python using Daft Dataframes. Maybe just a quick intro. So yeah, I'm a co-founder at Eventual Computing. Previously, I worked in biotech and self-driving, working on a lot of big data systems, but in these very interesting domains with very unstructured type data, not your usual tabular data, but also a whole bunch of timestamps and dates, and in addition to all the images and LiDAR and all that kind of data. I'm now a maintainer of Daft. That's our website, getdaft.io. And yeah, we are a data frame library. And so I found that usually the best way to just tell you what Daft is to just show you. Yeah, what is Daft, right? Actually, first I'll just go through the high level. So Daft is a batch query engine. It provides answers over your data. So for example, if you run SQL, right, that's analytics. You can run aggregations and group bys and joins, etc. It's a batch data processing engine. If you're running ETL, transferring one data set to another, Daft does that as well. It's a Python Dataframe API. That means if you're in the Python ecosystem and you're running ML and AI, that kind of stuff, it's very, very suitable for that. And last of all, it's built for distributed computing. And so it scales to whatever terabyte scale you need it to scale up to by running in the cloud on multiple machines. And so yeah, it's probably easier to show you rather than just tell you about it. Okay, don't worry, I've done the rain dance to pay to the demo gods. So hopefully this all goes through. But yeah, so Daft is completely open source. Here's our open source page, just like 1.7K GitHub stars. Yeah, you can very easily install Daft. And so I've actually done that in this notebook. If you do pip install get Daft, I've also installed it with a bunch of extra stuff for the sake of the demo. What you'll notice is that Daft is actually really small. It's all packaged within this one 16 megabyte binary wheel file. I actually compared this with Spark. Spark was 300 megabytes, So if I tried to do that on this Wi-Fi, this throttles me to 2 megabytes a second. That would have taken a long time. Daft is super lightweight. You just pip install it, and then you're ready to go. So yeah, to get started, you just run import Daft. I have an example here of how I'm reading an iceberg table from AWS Glue. I'm not going to run it because of the slow Wi-Fi, but yeah, you can run and read Glue tables. In this case, the iceberg table. We also have the ability to read Huddy, which I think Dipankar showed off a little bit just now. And then last of all, of course, Delta Lake. So Daft is compatible with reading all 3 table formats, which is really cool. And in addition to that, of course, we support all your different data use cases, right? So if you're trying to read CSVs, if you're trying to read Parquet, if you're trying to read JSON, lines, we also have really interesting ones. We're trying to read from a SQL database. We read from a whole variety of SQL databases. And so if you just want to grab data from a database, do some joins and do some analysis, you can do that. You just give it a SQL statement and you give it the URL to your database. Daft has a whole bunch of integrations there. A really cool one is also we just list files. So if you have a whole bunch of JPEG files lying around, like images, list them and then process them in Daft. And so here is an interesting one where Daft is one sec. Only need to rerun. Looks like I didn't do my rain dance correctly. My bad. Looks like I do have to run it from the start. Okay. Cool. So yeah, Daft is a fully featured query engine. And so we have a query optimizer, right? And so if you're reading this iceberg table and you're running, say, a filter, you can explain the plan. And here we have the plan. If y'all were paying attention during the Spark talk just now, that all these query engines have a plan under the hood. See that Daft does simple things like pushing down the filter into the scan operator. And so in this case, the filter gets pushed down into like a partition filter, which then Iceberg can leverage to give you really, really fast and efficient reads. And so yeah, now when you run the query, PyIceberg, which we leverage under the hood, it's a Python library, will leverage this filter to give you a much faster read, which is still slow on this Wi-Fi, unfortunately. Cool. And then I think what's really cool about Daft is that Daft also supports a whole bunch of what we call complex data types. So in this example, I'm just listing a whole bunch of JPEG images from S3. And then I'm going to convert them into images, right? So from this column of URLs, you can say, hey, Daft, run a URL download that converts it to a binary column. Then you can tell it, hey, Daft, convert it to an image column, .image.decode. And then now when you run this, Daft will be able to run this conversion for you on the fly. Everything here is written in Rust, and so it runs really, really fast. It's all proprietary code in Daft that like does this decoding for you, and it enables you to work with these data types really, really efficiently. Last of all, Daft is distributed, and so everything here is currently running purely in Python in a multi-threading environment. But if you need to scale up, right, if you want to process more data than what we just did, you can run it on a cluster using this framework called Ray. And so I'm going to show you how that works. So all you gotta do when you start Daft up, I'm gonna connect to an existing Ray cluster I have port forwarded on my laptop. And when you start Daft up, all you have to do is tell it set runner Ray. It will pick up the Ray connection. And now that query that I was very afraid to run before will run in the Ray cluster. And so it's much more efficient. And so it will say, it's going to be trying to scan about 14 gigabytes. I'm comfortable with that because this is running in the cloud now. And when I run this .collect, it's going to run that in the cloud on 14 gigabytes of data. And all you had to do was call one line command to like connect it to the cloud, which is really cool. So I'm going to let it run for a bit. But lastly, just for fun, I prepared this last night for everybody. Let's try running Daft in benchmarks against some of the fastest local engines that we have today, including DuckDB and Polars, right? So I'm going to run Daft on this side. So this is running a TPCH 10 gigabyte thing on my laptop. I want to see a vote. Who wants to see Polars? Okay, who wants to see DuckDB? Oh, a lot of DuckDB fans. All right, let's try DuckDB. So Daft is running on the left. All right, I'm gonna let it finish. It's going to come on, Daft, you can do it. All right, I'm gonna run DuckDB on the right, and we'll be able to just like do a rough comparison. DuckDB is obviously quite a bit faster, but not by much, actually, very surprisingly. And I have a graph that I ran last night, compared it against PySpark as well. And here's the graph. So you'll see that PySpark is significantly slower than Polars, DuckDB, and Daft. But between Polars, DuckDB, and Daft, you're actually very competitive. And what this means is that like you don't have to choose anymore between horizontally scaling and vertically scaling. You can actually choose both, because Daft scales really, really well vertically, right? Give us a big machine, we run fast. Daft also scales horizontally. Give us many machines, we run fast. So I thought that was really cool. Yeah, so that's it for the quick demo to give you a brief overview on what Daft looks like. And we can hop back over to the slides. All right. Okay, so yeah, let's talk a little bit about the higher level. Why should you care about Daft, right? So let's talk about Python and big data. Why not just use PySpark? So I searched on Google the other day, big data frameworks, and these are the results. If you look at every one of those entries, I think with the exception of Apache Kudu, which I searched, I think it's written in C++. The rest of them are all JVM-based engines, right? They're mostly JVM-based. But if you look at actual usage, this is a quote I found online from Reynolds at Databricks. He said, probably about 80% of Spark users use Python. And so I think we cannot ignore that Python is becoming kind of the new language for data, ML, and AI. And if you look at kind of this Venn diagram that I drew of like the three big use cases across analytics, data engineering, ML, AI, SQL falls very much so within analytics and data engineering, right? People use it often for that. It's really hard to use SQL for ML, AI. Python can do all three. I think it's maybe less so used for analytics, but it gives you the ability to do all three. And so we cannot ignore Python anymore. On the right there, I have a diagram from Databricks, which is the bronze, silver, gold medallion architecture. Data engineering happens very early on, and that's where we see a lot of usage of Spark, right, to clean up dirty data. And a lot of that is actually done in Python nowadays. And then on the tail end of that diagram, we have analytics in the little red section. That's very often done in SQL. But then you also now have the green section, which is ML, AI. And all of that's done in Python. And that's why I think we should all really, really start thinking about Python in the big data ecosystem. And let's take a look at Spark support for Python. This is a diagram that I pulled out about how Spark supports Python. It's fairly complicated because it is a very complicated architecture. There's a whole bunch of processes that are running. Processes are talking to each other over gateways. You have like JVM processes, and you have like these Python interpreters that are spinning up. It's very, very complicated, and there's a lot of moving parts and potential errors. So number one, when something goes wrong, you're like, oh, what went wrong? Did this, error out in the JVM? Did this error out in Python? Like, should I be worried? No one knows. Number two, there's a lot of data and memory overhead. Every time you're hopping across that boundary, you're copying data. You're like sending data between processes. It's really, really expensive. And also, who here has ever struggled with like S3, S3A, S3N? It's painful, right? Like this stuff wasn't built for the cloud. All of these protocols was our efforts to try and make it cloud compatible. But the reason Daft is so much faster is because we were built for the cloud and we were built for these protocols. And lastly, it's just a really painful local development experience, right? Once you're using Spark, any application becomes a distributed application. Now, by definition, you have all these processes and it's a distributed app. And so there's long startup times. And for anything that's like small to medium data, it's just really painful to work in Spark. Oh boy, this slide has really gone crazy. Oh my goodness. Okay, I guess I'll have to walk you through this almost based on memory. I'll try my best. But why do people still use Spark then, right? Number one, I would argue, I'm gonna move away from the slide because it's just confusing. But number one, I would argue is that Spark, for a long time, there was this data lock-in, right? Yes, our data formats are open. There's Parquet, there's ORC. But for a long time, the only way to read this stuff was through JVM libraries. Like the only good Parquet reader was a JVM one, until Arrow came out with a good one. And now this is accessible in Python, right? Number two, really the only engine that has powerful distributed execution is Spark. You kind of locked in there. Like it has really, really powerful shuffles, right? But I would argue that now with the advent of new technologies like Ray, which we use under the hood, these distributed shuffles are becoming very, very accessible. And so I think that like we're at a point where Python is finally ready to take on a lot of this big data workloads because we're seeing all these technologies come into play now. We're starting to see technologies like Iceberg, Delta Lake, and Hoodie also adopting Python increasingly. So let me move past the crappy slides. And here are some benchmarks. So these are the new ones. Our published ones are like 3.5x faster than Spark on a 1 terabyte benchmark TBCH. We're now about 6.8x faster. It's unpublished, but yeah, it's quite a bit faster. And this was all running out of core, right? The cluster we were using was fairly small. It did not fit all the data. And so there was a lot of spilling involved. And so it's very resilient to that. And we also see near linear scaling, which means if you double the size of your cluster, it's kind of like you reduce your wall time by half, which is really, really nice. And this was the little benchmark that I ran on my laptop. Yeah, if you're running just, like Polar's DuckDB size workloads, Daft is pretty good. We're actually better than Polar's some of them. DuckDB is a beast. DuckDB Q9 is really, really amazing. We have some crazy ass joins in there. But yeah, I mean, like Daft is comparable, like when you run it locally, which is really cool. So yeah, why are we so fast? Number one, vectorized execution. If you're familiar with projects like Gluten, Comet, Photon, Daft is built from the ground up like that. Like we are fully vectorized. Everything runs super fast on your CPUs. Number two, and this is, I think people don't appreciate this enough, is that there's a lot of I/O optimization that we do. Reading data is often the biggest bottleneck in your workload. The first thing you have to do to run your workload is get data into your system. And that's usually the most expensive part. And so we've actually worked very heavily with Amazon, teams at Amazon who use AWS and S3 to really optimize this using async Rust and retune for Parquet, CSV, and JSON files when you read them. And then number 3 and 4, we are built also with a lot of these query optimizations, metadata execution, things that you would expect a query engine would do for you. And Daft has all of that built in. And so maybe just a quick aside for the nerds out there, the architecture. So yeah, Daft, when you run it, there's kind of like a planning component and a running component, and everything runs within one process, right? So very, very much not like the Spark architecture. It all runs within one process. And when you run it locally, this is what allows us to give you that DuckDB Polars-like performance. Everything runs in one process. The only difference is that this runner leverages a thread pool to run. And so it's very, very efficient because memory sharing is very efficient. There's no crossing of process boundaries. And then when you run it distributed, the only difference in this diagram is that we now have this cluster that's serving as like the backend of your runner. And so yeah, everything still runs single process on your machine, but then now we're fanning out work over this cluster, which has workers. And this allows us also to give you out of core execution for any data sets that don't fit in memory, using a lot of arrays primitives to do that. So yeah, if you're interested in adopting Daft, here are some of the things on our roadmap. One that we're working in collaboration with Amazon on is how do we do these like giant, really giant shuffles to make sure that you're never gonna have a Daft job die on you. And so we're gonna be able to go out of band, outside of Ray even, to do these shuffles. Number two, and we're gonna run a lot of new execution optimizations. Sammy's in crowd. He actually built our AQE adaptive query execution prototype in like 2 days. It was actually really easy. I mean, I have a little screenshot of that happening there. You can't really see it, but what happened was we hot swapped the little broadcast join in there. Once we figured out, oh, the data is actually small, we can do a broadcast join, right? And so a lot of these optimizations can now happen at runtime inside of Daft, which is really exciting. And then we can also deal with a lot of the problems of automatic partition rebalancing. When you run Spark, oftentimes you're like, oh, how many partitions do I need, right? A lot of that's going to go away now in the coming few months. Number three, a lot of people have been asking us for SQL support. Yes, it's great. We're a Python data frame, but a lot of people are like, can I just run SQL on it? The answer is yes, in a couple of months, once we get to that. And this is also something we're thinking a lot about. Like, can we run Daft anywhere, right? This same model that I showed you, can we have these runners that can run us on, Ray? Yes. I actually ran Daft on Spark the other day. It was kind of funky. I ran Ray on Spark, and then I ran Daft on it. It worked pretty well. We can run on Yarn, K8s, EC2. We can even run on AWS Lambdas. Imagine kind of just the possibilities that this brings, right? You no longer have an entire team just maintaining your clusters. You just have these like dynamic things spinning up and down, and you just connect Daft to it and let it run. Yeah, that's it. That's all I have for the presentation today. This is our team, a small team. And we're actually hiring. So if you're interested in databases, distributed systems, hiring all across the stack, full stack, up to people who are database nerds, come talk to us. My email's down below. And that's it. Drop us a star. Thank you.
All right, Jay. Thank you for that great demo. I'll forgive all the digs on the LinkedIn Wi-Fi. I promise our real Wi-Fi is good. I guess our guest Wi-Fi is not so good. Cool, so let's go to trivia. Again, a little bit of a dig on LinkedIn, given that we're big Spark users, but let's talk about how much faster is Daft compared to Spark on the TPCH benchmarks. I think the first hand I saw was maybe that one. Yep. And that is correct. Great work. I don't know if you said that number or if you pulled it from the slide, but that was pretty good. Cool, and now we have a few minutes for Q&A before we wrap up. Yeah, go ahead and just turn on the mic before you start.
Hi, Jake. Can you talk about the use cases or developer persona you're targeting for, given this combination of Python API plus performance emphasized?
Yeah, so the initial, a lot of people are using us for these very Pythonic workloads that mostly include some sort of machine learning element, right? For example, if you were to try running a model that needs a GPU right now on Spark, it's a pain. Like, it's very, very painful. You have to try to figure out how to get Spark to allocate one GPU to your model and try to do all that distribution yourself. So a lot of people use Daft for that. They just say, hey, Daft, here's some data. I have all these transformations, joins. I'm running a model, and then the model produces some integer, and I want to aggregate over it. So that's a very common use case, people who are trying to run Pythonic things on their data. The other really common use case we've had increasingly come in is just very general data engineering workloads. Because it's so easy to run Daft, whether it's on a single machine or on a cluster, people are starting to run Daft just to be able to talk to Iceberg, talk to Delta Lake in a very Pythonic, easy manner, which in the past would kind of require a whole team to set up your catalogs and set up your Spark clusters, get all that setup done before you can even start working. Now with Daft, it's really easy and really performant in the cloud to do it. And that's an increasing trend we're seeing where people are just adopting us for cloud data engineering workloads.
Yeah, good talk. Thank you. So does Daft require integrating with a catalog, or how does it look up the underlying data?
Yes, great question. So the way that we integrate actually with Hoodie, Iceberg, Delta Lake, is all they do is they pass us file paths. And so we will pass them the pushdowns, where the user requested for these filters, the user requested for this limit. We'll pass that to these libraries. Then they can use their powerful metadata to prune out the files for us. And then they give the files to Daft. And Daft uses its really powerful Parquet readers under the hood to actually read those files. And that's how we're able to get that crazy performance, because we don't use a lot of the open source SDKs for like reading Parquet and all that. Daft actually has its own layer in there.
Extending onto that, like you talked about Rust as one of the performance gains, but all these table formats are still authored in Java and don't have a Rust implementation. So how do you, so is there multiple language hopping going on here?
The power of friendship. We are partnering with a lot of these libraries. So actually, I think we're the first distributed user of PyIceberg. The PyHoodie project actually lives in the Daft project right now. They're making PRs against Daft to build out the PyHoodie project. And then Delta Lake actually already had a Rust plus Python kind of shim layer. And so all these table formats are coming to Python. And a lot of it, I think, is making its way in there through Daft. What's interesting, and I think it's an opportunity for anyone out there who wants to build stuff, is that I think catalogs are still fairly fragmented. And so internally, we're thinking of building our own catalog kind of abstraction, like daft.set catalog. You can set it to like glue or something. But there isn't really a good abstraction for that right now in open source. But yeah, table formats wise, a lot of partnerships are happening. Things are really, really moving very fast in the table format world with regard to Rust and Python.
I have a similar question on that. So you mentioned these table formats, you're talking about like the Py version, right? PyIceberg, Py. When you showed the slide showing kind of the boundaries of Python and Rust, you showed the planning happens in Rust. So like, but the table format part is happening in Python? Where's kind of those boundaries?
Yes. So actually, Rust and Python interact very, very closely. Like they actually can run the same process. And so when we need to call out to the Python objects that we are passed in from these other libraries, we just have to kind of cross that barrier, but not cross a process boundary. So it's very lightweight for us to say, hey, grab the Python GIL interpreter, run some Python code, let go again. So that's kind of how we interact with these systems. But that being said, there's a lot of work actually going on now in, say, Iceberg Rust and Delta RS. And that means that we can fully integrate those crates, not libraries anymore, those Rust crates into the Daft core code without having to cross the Python boundary, which would be even more performant. I mean, right now, metadata isn't really the bottleneck for a lot of these things. And so Python is usually fine. But once you start getting to like 1 million files, for example, and a lot of that like heavy Avro metadata files, that's where we might be able to benefit from some of these performance optimizations.
But you mentioned that Daft is actually working on some of these, right? But you're working on the Python versions, not the Rust versions. Is that right?
Right now, we leverage the Python versions because a lot of the target audience for these new projects are Python because they want to unlock kind of the Python developer workflow. But under the hood, a lot of them are starting to build these abstractions in Rust with a Python kind of shim. And so technically, Daft could go one level deeper and use the crates.
Any other questions from the audience? Okay, well, great. Thank you again, Jay.
Thank you.
And I will pass it back to Swati to close this out.
Okay, can everyone hear me? Thank you. Can we have a big round of applause for all our amazing speakers? And thank you, everyone. I won't take more than 2 minutes of your time, I promise. I want to also give a big round of applause to the core team that's listed here. Sumedh and Eric, they worked doggedly with all of the internal and external speakers, herding cats and getting the talks done in time. And Christy and Allison are amazing admins in the back. They put together this entire event, all of the logistics. You can thank them for the food and the swag. Thank you so much. And Manisha also, like she's helped us like keep track of what slides were looking off, and and whenever we were off track, she really helped keep us on track. So thank you so much. It takes a village, as you can see. And so on that note, please take time to provide feedback. This will help us make our next meetup even better. I promise it's like 4 questions, I think. Shouldn't take more than a minute of your time. And then once you're done with the feedback, please stay back for these refreshments, mingle with the speakers and with other colleagues, and our recruiting team is back there. So please talk to them if you're looking for open roles at LinkedIn and you want to work on some of these cool projects that we saw here. Thank you, everyone. Thanks for your
I don't know where to start though.
Got to enjoy it as the audience that I could
I know, yeah.
Otherwise, it's harder